afternoon, dear Jeffrey Hedenquist and classmates. Now I'm going to introduce you to our classmates. This part I'm going to read in Spanish.
Bien.
Hoy la CGP presenta al doctor Jeffrey Hedenquist. Es un asesor independiente de la industria minera, exploración y evaluación de depósitos de minerales y epitermales. Trabajó en 45 países y para más de 135 empresas y agencias. Fue parte de institutos gubernamentales como Nueva Zelanda y en Japón, estudiando sistemas hidrotermales activos, así como la formación de depósitos epitermales de oro y pórfidos de cobre, y fue presidente de la Sociedad de Geólogos Económicos, la SG. En esta ocasión se presentará el tema Lithocaps y depósitos epitermales, más transición al ambiente de pórfidos, esto es formación, procesos y exploración. Dr. Hedenquist, you may begin with the presentation.
Thank you, Diego. Thank you also to Suker, who's administrating the host. And thank you to the SCG student chapter and students at UNI in Lima that initiated this conference. They invited a number of other chapters throughout Central Andes. So welcome to everyone, Ecuador, Bolivia, and anywhere else. Of course, the rest of Peru and anyone else who's attending. I'm going to have, let's see, I'll just get this started here. Let's see. I'm going to have to. I think I'm going to have to stop presenting and then start over again. A moment here. Okay, now I will start. There we go. Okay. Diego, can you see my screen fine?
Yes, doctor.
Good. I have to move this label. This is the first time I've used Meet. Let's see. I don't know all of the. Okay, try again. Okay, I'm going to discuss today the formation of lithocaps. I'll define what lithocaps are of advanced argillic alteration, shown here in the schematic by Dixilto. The shallow horizon, perhaps up to 1 kilometer thick, of advanced argillic alteration that may host epithermal gold deposits, and also the transition from the lithocap below into porphyry copper deposits. As defined by Lindgren, the epithermal environment is roughly 1 kilometer deep before we get into higher temperature environments. And this lithocap, which is shown in through here, advanced argillic lithocap, can be very huge in places. They may host epithermal copper gold deposits. Sometimes the copper is supergene oxidized, so it leaves the system. We have oxide gold. And on the margins of the lithocaps, epithermal polymetallic deposits, silver gold, rich, base metals, etc. And as I mentioned, transitions to the top of porphyry copper deposits, which are the source of 70% of the world's copper. So very important, not only in the Andes, but elsewhere in the around the world, as we'll see. And there are a variety of other deposits, porphyry proximal deposits, skarn in limestones. There are also carbonate replacement deposits further away from the intrusions, etc. I'm going to not discuss skarns. I know nothing about them. We don't have enough time today to discuss these other environments, but basically the lithocap, the epithermal environment, epithermal deposits, and down to the tops of porphyry. This is not a talk on porphyry themselves, but just the transition to the tops of porphyries where we might be able to explore and discover a deeper porphyry if the lithocap is eroded. Well, in 1973, Dick Silto was working in Chile, and he was working on porphyry deposits, but some of them, he recognized that the alteration was hosted by stratovolcanoes that had been partly eroded. And he argued that the active equivalent of formation of porphyry deposits is perhaps an edifice like a stratovolcano or a dome with abundant native sulfur. Here's the active volcano in Kyushu. And he argued that the effluents of the fumaroles, etc., are the active equivalent of the porphyry copper formation. And the reason that he recognized that, because there were many sector collapses of young volcanoes that were exposing advanced argillic alteration that he recognized related to the deeper porphyries. Well, this was not a very popular idea in 1973. The people in North America said, no, you're crazy. There are no volcanoes over porphyry deposits, et cetera, but Silto persevered. Of course, there were many more discoveries in Latin America, younger porphyry deposits, Southwest Pacific, etc., and started to see the clear relationship of porphyry deposits to their overlying volcanic edifice and the alteration and the epithermal environment. So I'll have a brief introduction here. We have several, as you can see, sections, and I suggest that at the end of each section, we will put them into chat for Diego to read at these breaks. Now, this is an active volcano, and we are going to look at the relationship between processes of active volcanoes and how they result in the generation of the alteration that we see in a variety of epithermal lithocaps and epithermal deposits. But first, let's take a look at one of the deposits at Yanacocha. Yanacocha is the largest high sulfidation lithocap-hosted epithermal gold district in the world, produced well over 35 million ounces of gold. Here, this is a young dome, about 12 million years, and you can see vertical flow banding here. This is clearly a volcanic dome. This was probably close to its original level. And if we take a look at the margins, we see finely laminated siliceous sediments. Now, this is not an altered rock because we see no phenocrystales, no lithic fragments, just fine laminations. And here we can also see cross-bedding in these laminated sediments, suggesting subaqueous deposition. Well, I should say that the dome is sterile, essentially not mineralized, but strongly altered. However, it's overlying a very large 5 million ounce gold deposit at 4 grams average grade. And so there clearly is some relationship to the deposit. Elsewhere in the district, we see other examples of fine laminations of siliceous material with fine clastic inner beds, and even in some drill core. these fine laminations. So what is causing those fine laminations? Well, if we move to the active environment, you can see here, White Island in New Zealand, high temperature fumarolic discharges from this passively degassing of active volcano, along with SO2 and HCl. And here, these fumaroles, very strong. I'm going to play a short video here. These are low temperature fumaroles, only a couple hundred degrees temperature. But when you're close to these, collecting samples, you cannot hear anything. They're so loud, huge energy discharging. Well, when White Island is not degassing, it's more quiescent. That vent is actually filled with groundwaters, but those groundwaters, rainwater, have a pH of 0.2, very acidic. And as the lake overflows and drains along this acid stream, slight neutralization, 0.6, but then when the acid waters flow into the ocean, we can see that this material here is basically isochemically dissolved rhyolite and dacite. Isochemical except for silica. The silica in this acid solution does not have high solubility, so it remains in the rock as silica residual. Also, from this lake, we can see this gray-green color. When the lake level lowers a bit, that silica, that gray-green color is due to colloidal silica in suspension. And that colloidal silica settles out, very fine laminated colloidal silica settles out of suspension. And here we can see in some places very fine laminations. Here was a block, either a volcanic bomb that came in and disturbed the fine laminations of the sediments, or maybe a block that fell in from the steep slopes, but then later on, again, more fine laminations. So that dome at Yanacocha, it was surrounded by a very acid lake with siliceous sediments depositing. Basically, that's the acid equivalent of silica sinter. Silica sinter forms from hot springs in neutral pH situations. But here, these are very acid. So if you ever find these finely laminated siliceous sediments, you know that those probably are related to an acid system near a volcanic center. Back to White Island on land now, and here I'm taking a photograph of Werner Gegenbach, who is a volcanic gas chemist. He collects samples of these high temperature fumaroles with SO2, HCl, CO2. Some of the fumaroles condense. The groundwaters condense the vapors. The SO2 combines with the water to form sulfuric acid plus some H2S. And that sulfuric acid plus the HCl results in a pH as low as 1, which can cause lixiviation of the rock. The fresh rock is completely dissolved, leaving only silica residual. And there's also then halos of alunite and kehlonite, other aluminum silicate minerals on the margins. We'll look at those details in a moment. Now, in addition to the very high temperature fumaroles with SO2 and HCl, there are also low temperature, 100-degree fumaroles on the margins. Those fumaroles only have CO2 and H2S. Now again, the vapor condenses above the groundwater table, and at that point, the H2S can oxidize with atmospheric oxygen to sulfuric acid. Again, sulfuric acid, but there is no HCl in these, So the pH is only about 2 or 3, not low enough to dissolve the rock, but still low enough to form kehlnite, alunite, etc. And depositing, as we'll see in a moment, horizons of opal. Here's another video I'll show of one of these steam-heated acid sulfate mud pools. The mud is kehlnite. The bubbles are CO2. So the H2S oxidizes to sulfate, forming the pH 2 or 3 solution that creates the kehlnite alteration of the volcanic rock, but the CO2 just bubbles through to the atmosphere. So this view was from Yellowstone, so if you ever get a chance to visit an active volcanic area and you see these bubbling mud pools, they're not boiling, they're simply bubbling. Okay, so let's go to La Coipa in central Chile, just northeast of Copiapó. And this deposit was discovered in the about 1980. The first deposit discovered was Ladera Ferion, which is a dome. It was outcropping. The sulfides were supergene oxidized, so we see strong iron oxyhydroxides here. And, I said 1980, sorry, 1990. And then subsequently, other deposits were found. First, Ladera Ferion, and then Cancan, Copia Norte, Brecha Norte, and Copa Norte. Well, I should first say that the residual quartz from, for example, Ladera Ferion, you can see the original dacite textures of the rocks, with the plagioclase finocrystales having been leached, lixiviated, to form this vuggy texture with addition of sulfides plus native sulfur. By contrast, over the top, close to the paleosurface, is this zone of steam-heated alunite and kehlnite. Basically a flat-lying blanket above the paleo groundwater table. And so there are two sources of acid alteration in this one environment, as we saw at White Island. Hypogene, high-temperature vapors with SO2 HCl, and low-temperature 100-degree vapors with H2S at the above the paleo groundwater table. And those steam-heated vapors, 100-degree vapors, they form this friable, porous rock with kehlnite, alunite, some opal, very different from the massive silica residual that's potentially hosting gold mineralization at depth. This is just a manto or a blanket over the top of the ore body. So, any questions so far on the active volcanic environment? Diego, do you see anything written in chat?
At this moment, there are no questions, Doctor.
Mm-hmm. Okay, well, we'll have another chance to ask questions in another 20 minutes or so. So please do, if anything is not clear, please feel free to ask questions. Grace has already seen these lectures in Bolivia last year, and in fact, she even translated some of these lectures, so she will be very familiar with these lectures, and she may have some questions or comments. Also, there are a few other people that I recognize names. They've been in previous lectures as well. Okay, well, we'll go on. And
Doctor,
yes,
there are questions from Jean-Pierre Alexander.
Thank you. Gracias, Diego. Hello, Doctor. Nice to meet you. I have a question about the picture of Yanacocha. I would like to, I want you to repeat it, the explanation about that picture, please. Because you talk about the flow banding, but I didn't see it.
Not flow banding. Well, here, sorry, this is a dome. Very clear vertical flow banding. You can see when it's a very viscous lava and it's rising up and then it flares off near the surface. And on the margins of this dome, there was lower angle flow banding. So typical style of flow banding in near surface domes, very highly viscous magma. And then the laminations here in these siliceous sediments. Okay, same here. So two different, this is actually not banding, these are just laminated sediments. Okay?
Yeah, thank you, Doctor.
Anything else? Okay. So, this is a map showing the extent of Miocene, Pliocene, epithermal, and porphyry deposits, some of the major ones, around the Southern Pacific, here in Latin America, up through North America, down through the Western Pacific. And you can see the close spatial relationship between epithermal in yellow and porphyry in blue. So at least we know that there's a spatial relationship. And if we go back further in time, Jurassic, Eocene, Tethyan arc from Indonesia through Myanmar, Tibet, in through Central Asia here and Turkey, etc. There's still quite a few deposits because there's fairly good preservation of that upper kilometer or two, although you can see that there perhaps are lower proportion of epithermal maybe, but this is not statistically, these are just some of my favorite deposits. And then we go further back into the Paleozoic. And if the older rocks have been preserved, the shallow level, 1-2 kilometers, have been preserved from erosion, it's possible to have even Paleozoic porphyry and epithermal deposits. I'm working on epithermal deposits in southwest Mongolia right now, 320, 330 million years of age. Same along the eastern coast of the US. We have Jurassic aged deposits here in Argentina, Patagonia. And then even in places, there are Paleoproterozoic epithermal deposits, but they are metamorphosed. Up here in Fennoscandia. And I skipped over, should have mentioned that there are also, these Neoproterozoic deposits in Arabia. Okay. Now, this orientation of porphyry and epithermal along the Circum Pacific volcanic arc, of course, is related to the fact that there's an association between the volcanoes, the epithermal deposits, and the deeper porphyries. Here in the Sunda and Banda arcs of Indonesia, we can see Merapi now active. Let's see, Merapi, I think this one here. And yet, if we look back into the late Miocene, Pliocene age, the arc is actually shifted to the north with time. The present arc is further active arc is north of the Miocene, Pliocene arc. And we see a number of red dots, porphyry, large porphyry deposits. Black dots are smaller porphyries and a variety of epithermal. These are in eroded Miocene, Pliocene volcanic centers. The colors reflect the topography, the elevation. So you can see the nature of the erosion here. And with 4 world-class porphyry deposits, all discovered in the last 25 years or so. First, Badahijiao, then Ilang, Hu, or Onto, and Tupangpitu. They are very large deposits, 7 to 15 million tons copper, and with 500 to 800 tons of gold. And throughout the arc, there are pairs of porphyry and lithocap deposits circled with the white areas. So there may end up being more large porphyry discoveries as they are drilled, particularly on the island of Java. So at least we see this, again, spatial relationship here in Indonesia, and some very young epithermal deposits and porphyry deposits at Hu or Onto. This area is as young as 400,000 years only, still very hot. Now, what's the reason for this, at least spatial relationship? Well, clearly, during subduction and partial melting, slab dehydration, partial melting, in volcanic arcs, continental hosted volcanic arcs, we have magmas rising through the thick crust, magma reservoirs, and at shallower levels, porphyry, and at even shallower levels, epithermal deposits. These are the polymetallic epithermal deposits with spatial transition to porphyry copper, copper gold, copper moly. Now, there are also other styles of epithermal deposits that we're not going to discuss today, not enough time. They form in zones of extension, maybe back arc zones of extension. However, they do not have underlying porphyry deposits. The porphyry deposits are focused in the accretional, in the volcanic arcs, either continental, like in Latin America, Andes, or like in Indonesia, Philippines, etc., in oceanic arcs. Now, this is very simple end member, but as you can see from this image, some things don't make sense. Has anybody ever seen a nice apple skin with a orange interior? Naha? Looks interesting. But the question is this a hybrid? Has someone done genetic manipulation to come up with a hybrid orange with an apple skin? Or is this simply an overprint? That the first was an orange and then there was an overprint of an apple skin? And that's a question for many epithermal systems. Sometimes we see different characteristics. Are they simply a hybrid between two end members, like these polymetallic veins and the extensional veins, or are they an overprint? And that occurs very often. So again, I won't have time to go into all of the details. That's a 1 day or a 2 day short course, but at least keep that in mind, that not all of the examples fit nicely into end member boxes. We have many hybrids as well as overprints. Agree that there's a relationship between volcanoes, epithermal, and porphyry in volcanic arcs. People didn't accept it at the time. Most people now accept it. I think there are perhaps still a few people who don't, but they're not simply observing reality. Silito has come up with a new model, a little bit more detail, published in 2010. I can send this, if people don't have this paper, I can send it out after the lectures. And the question is, why do we see this relationship between porphyry deposits and lithocaps and possibly some epithermal deposits, epithermal metals? Well, because magmas at depth exsolve a fluid as they crystallize. We call this a critical behavior fluid. It might have 5 to 10 weight percent sodium chloride, and also up to 0.5% copper. Here we can see this tetragonal sulfide, opaque, it's a sulfide. This is chalcopyrite. So this is the parent fluid. Now, as this fluid rises from the magma, it reaches 2 or 3 kilometers depth, and the lower pressure results in separation. We say that the fluid intersects its solvus, but it separates to a very high salinity hypersaline brine, 50, 60 weight percent sodium chloride, potassium chloride. You can see the halite and the sylvite here, the iron chlorides, etc. But the only way to go from 10% to 50% brine is to remove a huge amount of vapor. And by taking the water out of the liquid as vapor, that concentrates the salts in the liquid. Now that hypersaline brine is very dense, so it stays at depth and forms potassic alteration, but the vapor has a low density, and therefore it can rise towards the surface. And in fact, at White Island and many other passively degassing volcanoes, we see that vapor discharging along with various gases from the magma. But some of that vapor, as we already looked at White Island, some of the vapor condenses into a very acid condensate, pH less than 1, that causes lixiviation, formation of residual quartz, as well as halos of quartz alunite or quartz kaolinite. So that is the fundamental relationship between the lithocap and the underlying porphyry. It's that brine and vapor formation with the vapor linked to the brine, but the vapor rises, condenses, and forms the lithocap over the porphyry intrusive system, generating this lithocap at shallow depths. And as I said, the brine and the vapor are linked. They're coupled. We cannot have one without the other. This vapor is not coming directly from a magma, and the brine is not coming directly from the magma. This critical behavior fluid is what comes from the magma, and it's the process of depressurization and separation that causes the two different fluid components with different alteration characteristics. And then once we have the lithocap, it may be mineralized with gold and copper, or in fractures, epithermal polymetallic veins on the margins. At depth, porphyry copper, and of course these other styles of mineralization we already looked at. And as the mineralizing liquid rises, there's a transition from white mica, muscovite, to pearlite at the base of the lithocap. So I'm going to show examples of this later in some of the case studies. So, do we have evidence, though, for an epithermal deposit directly linked to a porphyry deposit? Spatially, yes, but what about in terms of time and genesis? If we go to northern Luzon in the Philippines, where I've worked for quite a while, we can see here in the Mankayan district, these cliffs are quartz alunite, very resistant to erosion. Here, more cliffs here, and all along here, we see cliffs of quartz alunite for 7 kilometers exposed by erosion. Well, those cliffs form right at the unconformity between the basement volcanic rocks, volcaniclastics, and the overlying pyroclastic rocks. So that horizon was permeable. Condensates were able to leach the the permeable unconformity and result in this quartz alunite lithocap. And there are deposits. One is the far southeast porphyry deposit, and Lepanto is the enargite gold deposit. Here we see the present surface. This is a long section through Lepanto, showing the projection of the FSC porphyry, some veins. This is the volcanologist working here, has reconstructed the surface at about 1.5 million years, only 100 or 200 meters of erosion. The porphyry was recently drilled out from underground to below sea level, and this contains 890 million tons of ore, 600 tons gold, 5 million tons copper. The orange is 1% copper grade shells, the yellow 0.7 grams per ton gold grade shells, and the blue is the 100 ppm molybdenum grade shells on the margins. Well, the biotite potassic alteration related to the formation of this porphyry is 1.4 million years. We have 6 dates by Antonio Arribas. Well, we know that vapor would have been discharged at that time, but some of that vapor condensed to form this pink quartz alunite lithocap along the unconformity. And that quartz alunite, or the alunite, also has an age of 1.4 million years. 5 alunite samples from over the top of the porphyry to 2 kilometers away. The potassic alteration and the alunite are the same ages. Why? Because potassic is related to the brine, biotite related to the brine, and the alunite related to the vapor condensate. Very simple. Subsequently, the introduction of metal-bearing liquids. I should have said that this lithocap was sterile in formation because there are not high concentrations of metals in the vapors. Subsequently, a liquid ascended from the porphyry, chalcopyrite stage liquid, and the white mica at one point dated at 1.35 million years, 8 samples there, 10 samples, transitioned to porphyte and entered the lithocap, depositing the enargite and the gold. So not only are these 2 deposits temporally or time related, they are related in terms of genesis. So this was perhaps one of the best proofs of a relationship spatially, in terms of time, and in terms of genesis. Relationship of porphyry to the lithocap and to the lithocap-hosted high sulfidation enargite gold mineralization. And also, slightly younger, less than 1.3 million years, for formation of polymetallic epithermal deposits on the margin of the lithocap. So it's all here. Everything that was in Silito's 2010 model is right here. This is reality. So with that, any questions?
Yes, doctor. There is a question from Aldo Bendezul. Are there discernible differences in terms of geochemistry, size, or mineralogy between lithocaps associated with copper-gold porphyries and those associated with copper-molybdenum porphyries?
That's a good question. What's the difference between copper-gold and copper-moly lithocaps? I'm coming up to one slide, and molybdenum-rich porphyry copper deposits tend to form very deep based on observations. And I've never worked on one. I'm not familiar with the nature of the lithocap. of moly-rich porphyry copper deposits. I'll ask Dick Philito if he has any comments, but for example, some of the major copper moly deposits that I'm thinking of, I can't think of a preserved lithocap. There's one in Mongolia where I'm working on. It's actually, moly is greater than copper, and it's eroded down below the lithocap level. So I'm afraid I can't answer that. However, certainly the difference, there does not appear to be a difference between copper-only porphyry lithocaps and gold-rich porphyry copper lithocaps. But that's a good question, and I'll try to get an answer, or at least comments, and send the answer to Sukur in a day or two, okay? Any other questions?
Yes. Juan Sebastián Duran have a question. Please.
Hello. Thanks, Dr. Jeffrey. I have a question. Why the silver and the base metals are enriched in the distal zones? And this is a rule for every epithermal and porphyry deposit, and even the intrusion related. It's a temperature thing, or? Well,
they're not necessarily enriched, because we can have some very silver-rich high sulfidation deposits. For example, Veradero in Argentina, Pascua Lama in Chile and Argentine border. These are sometimes in places they have 100-to-1 silver-gold ratios. La Coipa has 100-to-1 silver-gold ratio. By contrast, some other porphyry deposits, high sulfidation gold deposits in Peru, they tend to have closer to 1-to-1 silver-gold ratios. I don't know the reason for the difference in the silver-gold ratio, but in terms of, so basically we can see gold and copper mineralization in the lithocap, and I think the copper in the lithocap may be due to higher salinity fluids bringing the copper, whereas we tend to see lower copper in the epithermal veins on the margins of the lithocap, and tend to have higher lead zinc. Now, yes, you mentioned temperature. Some of the modeling done suggests that lead and zinc are transported to lower temperature parts of the system. So they deposit on the margins. And we see this around the world, that often in porphyry copper districts, there are lead zinc veins on the margin. Sometimes they're low in gold and silver, and sometimes they're rich in gold and silver. I don't have a good answer to that question, except that the gold, silver, lead, zinc tend to transport to lower temperature margins. There's a paper by Kalin Kuzmanov in the 2012 Silito paper, silicium on gold deposits, that discussed this. So again, cannot give you a good answer, but your suggestion of lower temperatures is certainly important in the epithermal environment. Okay, any other questions?
Yes, Miguel Ponce asked, do we have sinter deposit related to both high sulfidation and low sulfidation epithermals? If yes, is there any way to difference between them in the field?
That's an easy question, because the answer is no. So we don't have to worry about distinguishing. Silica sinter only forms at a near neutral pH. Why? Because under acid conditions, silica does not polymerize. Polymerize means to grow. And so we do not get any silica sinters around lithocaps. But as I showed, there is colloidal silica that forms in acid crater lakes. And eventually the colloids grow large enough and they settle out by physically settling and forming the fine laminations. So the finely laminated lacustrine sediments, siliceous lacustrine sediments, are the equivalent, if you will, of silica sinters in the low sulfidation environment related to neutral pH hot springs. Basically, there are no neutral pH hot springs in these near these vapor condensates. They form far on the margins, several kilometers after the acids have been neutralized. So no silica sinters. If somebody tries to sell you a lithocap hosted high sulfidation deposit with silica sinters, you know something is wrong. I've actually seen that described in one prospect in Chile. Something was wrong. It's not a sinter. It's not a lithocap. Perhaps it's none of the above. I don't know. I didn't look at that prospect, but that was a description of it. Okay, I hope that clarifies that a bit. Any other questions?
Yes, there are two more questions.
Okay.
Sahira Martinez asked, which dating methods were used on biotite, mica, and alunite?
Yeah, the only dating method that's possible of those relate to argon. In fact, those were done by potassium argon rather than argon in the best laboratory in Japan. And the reason being that Japan doesn't have any nuclear reactors that can irradiate samples to cause an argon 4039 signature. So Antonio had to use potassium argon, but still he had 40 to 80,000 year 2 sigma errors. Very, very narrow error bars because it was such a good laboratory. And he had extremely pure samples to work on. So if you have a potassium-bearing mineral like alunite, like white mica, like biotite, then you will go with a argon or even potassium argon analysis. Whereas if you have a rock with zircons, then you can do uranium lead dating. If you have molybdenite or maybe some sulfides, you may be able to do rhenium osmium dating. Very high precision to rhenium osmium, but also high cost. Maybe 10 times more expensive than, 5 to 10 times more expensive than argon dating. So, okay. So it depends on the samples that you have. And you said one more?
Yes, the last question is Paul Buenano asked, how can we know where is situated the porphyry and epithermal? Maybe is there any geochemistry or geophysical property? I talk about when in surface we cannot see any proof or epithermal or porphyry. He means to the lithocap.
Yeah. I will present something very briefly. I'm not a geophysicist, but I will present some geophysical signatures later, so we'll wait for that part. Chemically, we look, and I didn't put in the details because of time, but higher temperature minerals, we'll again come to that a little bit later. Porphyte dictite, that's forming proximal position. Kaolinite forming distal. If we have sodium-rich alunite, that forms proximal, higher temperatures. Potassium-rich alunite forms distal. But there are so many variations. I've seen so many different examples that I don't give simple recipes for if you have this geochemical association, you are proximal. If you have this geochemical association, you are distal. You really have to assess every situation case by case with some good examples, case studies, giving ideas. So that's why I don't like to give any simple recipe. But we'll be coming to a few discussion points later in the lecture that hopefully will better answer your question. So we'll leave that for later, okay? Is that fine, Diego?
Yes, there are no more questions.
Good. Okay, we'll move to the next one. We'll take a look at some lithocaps. Here in Japan, there are a large number of active volcanoes shown in red triangles, and most of them have, shown in green, magmatic hydrothermal systems on their flanks. And those magmatic hydrothermal systems are, of course, related to the vapors condensing, et cetera, et cetera. And some of these volcanoes have had recent magmatic hydrothermal eruptions, or just hydrothermal eruptions. For example, Kusatsu Shirane and Otake. During these eruptions, the ejecta has thrown out kaolite and pearlite. These are aluminosilicate minerals formed in lithocap situations. Other cases, alunite, kaolite, pyrite, and pearlite. And then also quartz muscovite, chlorite, and quartz feldspar, K-biotite. That suggests that at Ontake, that eruption in 2015, I think, or 14, may have extended down to the potassic level, more than 1 kilometer deep. So here at Kusatsu Shirane, here's one of these hydrothermal eruptions, cristobalite, kaolite, pyrite, alunite, pearlite. Exactly the assemblage we're going to discuss now in some of these lithocaps. And let's see. Yeah, these are some of the volcanoes, volcanic hydrothermal systems, Kusatsu, Kirishima, Satsuma, Iwajima, that have had recent hydrothermal eruptions. So let's go to Satsuma, Iwajima, just south of Kyushu, and then we'll move on land and look at some lithocap-hosted deposits called Nansatsu gold deposits in southern Kyushu. This is a rhyolite dome erupted about 1,000 years ago called Satsuma Iwajima. Iwo means sulfur. Jima means island. So there are many volcanoes in Japan, as well as the infamous volcano Iwajima, that have that name because they're capped with sulfur. Here, this is from the Satsuma region. And we've collected samples of the high temperature vapors, up to 800 degree temperatures, SO2, HCl, but only 1 to 2 part per trillion gold. So as I mentioned, the vapors can alter the rocks if they condense, but they're not transporting very much gold. And again, this reaction, SO2 combines with H2O to form or disproportionate to sulfuric acid and H2S. The sulfuric acid and HCl then dissociate at lower temperatures. And that's going to be important because at high temperatures, those acids are associated. If you remember to your high school and university chemistry classes. But at lower temperatures, those acids start to dissociate and become more reactive. And below 250 degrees, these fluids can have a pH as low as 1. And that's why there are acid springs along the shores here, pH 1.1 to 1.7. And they're dissolving the rock, and that's why we get this discolored water around the ocean margin. This rock, this rhyolite has been dissolved up to 97% residual silica and alunite, but almost all samples are less than 2 part per billion gold. Only one sample, 29 ppb gold. And that probably was close to a fumarole related to some sublimates. Here is Werner Gegenbach again, that volcanic gas chemist, looking at this rhyolite. And the reason he's looking at the rhyolite is because of the geochemical processes to result in 97% silica. Complete lixiviation of the rock, just a little bit of titanium left behind. But as I said, it's sterile. Lixiviation seldom results in any more than a few tens of ppm of gold anomalies. Anomalous, but nothing that's going to cause any significant economic mineralization. Now here is Satsuma-Mishima on 50 kilometers south of Kyushu, formed from 1,000 years ago to present. And on land, we have the Nansatsu deposits, lithocaps of about 3 to 4.5 million years, quartz alunite and residual quartz. So let's take a look at some of these. They also host gold deposits. Here are these three deposits, Akechi, Iwato, and Kasuga, 3.7 to 4.5 million years. Andesite hosted, volcanic rock hosted, but there was a nearby caldera eruption of 70,000 years ago of ash, volcanic ash, that filled in the low areas here, completely covering the altered rocks. But in places, we have, for example, Tsunomi volcano. It's largely barren, but has several lithocaps of residual quartz, silicic alteration, and also some quartz alunite in orange, shown here. And the reason that these stick through the ash deposits is because they were resistant to erosion. So they're forming topographic highs. So let's now take a look at Iwato. And here we see this is all residual quartz. The pyrite has been supergene oxidized. So it's largely a supergene oxide gold deposit. And it's about 900 meters long of residual quartz with narrow margins of quartz alunite and quartz kaolinite in orange and yellow. And here we can see the margin, very sharp, almost you can put your hand on the contact of residual quartz and quartz alunite. And through here. And right here, we can see this feeder zone rising up and then flaring outwards. And if you look at the plan map, it looks like this is one silicic body with 1 gram per ton gold ore bodies, several smaller or larger gold ore bodies. But if we look at a cross section, we see something different. At depth, the rocks are andesite, lava flows. And there are fracture-controlled structures controlling the alteration because the andesite lava flows had low permeability. But when the fluids, the vapor condensates, rose and reached this level of this airfall tufaceous horizon, the tuff was permeable, and so it was able to form a lithocap. So this was the first recognition of lithology-controlled permeability to the alteration. That was basically the origin of the term lithocap. Lithocap is the lithology-hosted, permeable lithology-hosted advanced argillic alteration cap to the underlying part of the system. Here at one of these deposits, we see the residual quartz here. Here we can see the residual quartz, the vuggy textures, some lithic fragments in this tufaceous deposit, et cetera, et cetera. There's even some fiamme in through here. And then the vugs are filled by sulfides as well as native sulfur. And then the residual quartz, vuggy texture residual quartz, was fractured. And after fracturing, there was a colloidal silica gel that informally we call creamy silica. It's not a good term, technical term, but that's what it looks like, creamy silica, and that's the gold event. The high-grade gold that we'll see in a later example is associated with this cement of the barren residual quartz. Here again, we can see in another example, this is of this creamy silica. Here was a 109-meter intersection with averaging 6.4 grams gold, associated with this brown to creamy colored colloidal silica with laminations. Okay, moving from southern Kyushu, where we started at this active dome, then we moved to on land to look at 3-4 million year old deposits. Now we're going to go to the origin of the term vuggy quartz. It was called vuggy silica in 1960, but this is Summitville in Colorado, the US. Here is a large dome that is hosting alteration along structures. Now the dome margin is shown through here with plus marks. It's over almost 1 kilometer in diameter or even more, but it's dominantly quartz kaolinite. But along structures, we have residual quartz and quartz alunite shown in red and orange, and high-grade underground stopes mined before 1950, grades of greater than 10 grams gold. And you can see the very strong structural control to these high-grade stopes. Well, in the 1980s, a company came in, decided that they liked this, so they were going to mine this by open pit. But look, all of the grades were they recognized the high grades. They thought they were going to be able to get those grades in open pit, but all the grades were along the structures. In fact, half of the high grade had already been mined, or I should say most of the high grade had been mined. They only produced a small amount because there's very, very low grade halos around these structures, 0.3 grams per ton in the blue halos, very narrow halos to those structures. And here you can see one of those structures of residual quartz with symmetric halos of quartz alunite on either side, and then out to kaolinite and dickite. We'll discuss that in a moment. Here is a close-up of the contact between residual quartz and quartz alunite. Here is the monzonite dome with 2 centimeter large feldspar phenocrysts that have all been altered to alunite. Alunite is stable at a pH greater than 2, whereas alunite and aluminum silicates dissolve at pH less than 2. Aluminum becomes soluble at pH less than 2, and that's why we end up with this residual quartz, because everything else is dissolved at pH less than 2. And you can see how sharp this contact is. pH greater than 2 to the right, pH less than 2 to the left. Well, the reason for that is a very simple stability diagram. This is sulfate and hydrogen activities plotted along x-axis and potassium sulfate along the y-axis. Lower pH, greater hydrogen activity will mean lower pH to the left. So if we start at high pH, we're K feldspar stable. But as the pH decreases, first move into white mica, then kaolinite or dickite, perophyllite at higher temperatures, and finally below pH 2, aluminum is soluble, and so we get to residual quartz stability. That's the reason for this sharp contact between alunite stable and alunite being dissolved right through here. Alunite forms where there's enough potassium present, because of course alunite is potassium aluminum sulfate mineral. Kaolin and dikite, perovskite, are simply aluminum silicates. So they form at lower potassium concentrations. And so if we have a very acid condensate, as it reacts with the wall rock, slowly the halo might go through alunite, then kaolinite or dikite, out to clays, and finally to fresh rock, K-feldspar, simply because the acids are being neutralized by reaction with the wall rock. This shows a view at Somerville. Unfortunately, it snowed the previous night, so all we can see is snow, but this, where all the geologists are standing, this is the residual quartz ore body. So the geologists are looking there. A couple of geologists are looking at the quartz alunite margin and through here. But you can see how resistant residual quartz and quartz alunite is, and then everything else, very steep drop off in the clay alteration halo. Now, Stephen Ratte, who did the original study in 1960, they worked underground. So they recognized that the residual quartz expands upwards, gets thicker at shallower levels, and the quartz alunite halo becomes wider. Why is that? We see that now in almost every deposit. Along structures, they flare upwards. The simple argument, or the simple reason, is that at shallower levels, the temperature is lower. At lower temperatures, the acids dissociate. And the dissociated acids at shallower levels are more reactive. And so we get this upward flaring zone of alteration. Now here at Summitville, there's no permeable horizon. So that's why this is such a small deposit. It's only restricted to the fractures through the monzonite dome. I should also say that another change, we see tennantite and chalcopyrite at depth, but at shallower levels, so there's also a shallower transition from intermediate sulfidation sulfides to high sulfidation state sulfides. We'll look at that in the next slide with a phase diagram. So, intermediate sulfidation, by definition, is tennantite, chalcopyrite, tetrahedrite. Chalcopyrite, pyrite, tennantite, these are intermediate sulfidation states. Enargite, pyrite plus bornate, or covalite, high or very high, whereas low sulfidation states are arsenopyrite purtite. Bornite and magnetite in the high temperature part of a porphyry are also low sulfidation states. So how do we interpret these mineral assemblages? Arc magmas are relatively oxidized and they start off low sulfidation state, but the fluids at 800 degrees, but the fluids exsolved as they cool to intermediate sulfidation state. The rock itself, the buffer of the fresh rock, has an oxidation or a sulfidation state following this yellow line. Basically, the rock is low sulfidation state. As you might expect, you extend this up, the original magma was low sulfidation state. So as the fluids cool through 500 degrees, they pass through bornite and magnetite, as we see in the deep part of porphyry copper deposits. And then they, at lower temperatures, approaching 300 degrees, they reach chalcopyrite and pyrite stability. And because of the reaction with the wall rock, the fluids basically stay in chalcopyrite pyrite at lower temperatures, 300, 200 degrees. They stay in the intermediate sulfidation state because those fluids are reacting with fresh rock on the margin. However, what happens if there's a lithocap? If there's a lithocap, all of the iron silicates have been removed. The buffer of the fresh rock is no longer present in the lithocap. In that case, if fluids are cooling and reach the base of the lithocap, they will evolve into high sulfidation state stability, enargite stability. So that's a very simple explanation for why we have enargite gold deposits hosted by residual quartz lithocaps. There's no rock buffer. If there was no residual quartz lithocap, there would be very little enargite deposits. Very simple. Here we see at Goldfield in Nevada, very high grade deposit, mined average about 20 grams per ton gold in the early 1900s. Here we see native gold along fractures. The residual quartz vuggy has been fractured here, cemented by leuceinite. Leuceinita is the dimorph of enargita, the same composition, just different crystal structure. And we also see covalite, covalina, which is also a high or very high sulfidation state mineral, cementing the brecciated barren residual quartz, along with the native gold. We're not going to talk about magmas and rifts and low sulfidation deposits, but basically that's why low sulfidation deposits are called that, because they have pyrite, pyrrhotite, arsenopyrite, and they basically are formed with less relationship to a shallow magma. Okay, but the main thing is to focus on this environment. Now, to summarize this concept, we have structurally controlled feeder zones where vapor condensates are dissolving the rock at pH less than 2 with quartz alunite halos, where the pH increases on the margins. And as those fluids rise and cool, the acids dissociate, the fluids are more reactive, and we get this upper flaring. If the structure conduit intersects a permeable lithology, we can then get a lithocap forming. And all lithocaps have structurally controlled feeder zones. There's never a rootless lithocap. There's always some structure, some margin of a dome, perhaps a margin of a diatreme, some structural cross-cutting feature that guides the feeder zones. And these zones, again, they flare upwards. Remember also, we have a different type of acid alteration, the steam-heated alteration, these mantos of kaolinite, alunite along with opal. That's simply related to H2S, oxidizing to sulfuric acid. Now, if we just leave it here, we have a sterile lithocap. Has all the characteristics of a mineralized lithocap, just no metals yet. But fortunately, if the lower salinity fluids rise from the porphyry, they can mineralize the portion of the lithocap. And where they do, the feeder zones always have the highest grades. And the lower grades are in the more distal parts of the lithocap. And then we can have sterile parts of lithocap kilometers away from the actual ore body. This all takes good mapping of the lithology, of the alteration, etc., to be able to find the root zones, the highest grade portions of the deposits. And this is what we're looking for. We're looking for the stages where gold has been introduced in the second stage, after the sterile residual quartz formation. So perhaps there are some questions now on that.
Yes, two questions. First,
Sure.
Aldo Bendesu asked, it has been suggested that halogens enhance the fertility of porphyry systems. In this context, are lithocaps enriched in fluorine-bearing minerals like topaz or sunite indicate or of larger thermal of porphyry copper deposits? How conspicuous are these minerals in lithocap? Are they always found in lithocaps?
Well, first of all, yes, we often get fluorine, chlorine-related minerals forming, zunite, topaz. Commonly, they are relatively minor, and many people have difficulty recognizing zunite with a hand lens, but it's relatively easy to identify with shortwave infrared teraspec. More importantly, sometimes, though, are the minerals that are based on the alunite structure, the aluminum phosphate, sulfate minerals. They can have high rare earths, crandallite, woodhouseite, those minerals. And again, very difficult to recognize, well, probably impossible to recognize with a hand lens. There you can perhaps identify them in thin section or by X-ray diffraction. And they're quite common, more common than we probably realize because they're so difficult to recognize. Again, the zunite, perhaps more easy to recognize if it's coarse enough crystals or if you pick it up on shortwave infrared. I've never seen any difference even in lithocaps without these minerals. So I don't know if they reflect quote unquote fertility, and I'm not sure if they really reflect fertility in porphyry deposits. I've seen porphyries with no evidence for fluorine minerals, and I've seen others with evidence. So I don't know. I don't work on that field, so I wouldn't want to say one way or the other, but I've not seen clear evidence for that. Certainly, if one of those minerals are present, you should look at it, because at far southeast, the APS minerals, aluminum phosphate sulfate minerals, tend to be focused proximal to the lithocap, not so much distal. You can read a paper by Zhaoshan Chang and others that we published in 2011 on the Lepanto lithocap. And we also look at APS minerals in that paper. So, Diego, do you have any others?
Yes, Santiago Bentacur asked, the reason why gold is concentrated into the baggy silica zone is only because of pH?
No, not because of pH directly, but more indirectly, because the vapors condense, and of course they have to follow a zone of permeability. The first permeable zone from depth is from structure. But if we have a lithologic horizon, then they may flow off along that permeable lithologic horizon. And as they do, they cause lixiviation, which can increase the permeability. But also, that serves to make the rock very brittle. And as you saw in a few examples, that brittle rock then fractures easily, and the fluids can flow through and deposit gold. Whereas if we have rock altered to kaolnite, or other clays, that rock is not going to fracture very easily. The kiln-like dominated rock is going to be very impermeable. So the acid alteration helps to lead to porosity and permeability, and creates a very brittle, easily fractured rock. So that's one reason, because in fact the metals in the lithocap come in during the white mica stage, and those fluids are probably pH of 4 to 5, not a pH of 1 or 2. So that was what I would how I'd explain that. Okay.
Okay, and the last question is with Denison. Can you please open your microphone?
Yes, thanks for the past. Okay, my questions are about what information is there in Peru about the contribution of dacitic, rhyolitic, porphyries of the Neogen period in forming epithermal systems? Because these bodies cut through the entire Paleogene volcanic sequence. In general, I could see through the spectral image anomalies of clays near to this contact. In addition to this, I was going to these ecologies near to the contacts, and what is most manifest in outcrops is silification together with veins of dark oxides and presence of kaolinite in membranes. And what is and with this information, what do you think? In what part of the epithermal system would I find?
Well, it's good to have indications from satellite imagery, spectrometry, etc., to indicate alteration. But once we have those indications, of course, we simply have to do a field check, and we then have to map out what is the lithology, what are the intrusions, because as you point out, there are a lot of rhyolite dacite domes, and they are very strongly related to mineralization. Yanacocha is a district, is a series of at least 20 different domes. Some are closely related to mineralizations, others are not, at least spatially. I'm going to show a few more examples of some dome-related mineralization in Peru, etc. But once we find an altered area related to a dome, well, we simply have to map it out. If we have a lot of iron oxides, that will reflect, of course, oxidation, supergene oxidation of sulfides. But we have to look at the underlying pre-supergene oxidation, pre-supergene alteration, to find out what the primary alteration is, what its mineralogy is, what its zonation is. And I can't generalize. We simply have to go into the field, use our geological training that many of you are students now and are getting right now, get into the field and start mapping and put together things so that you can start to say, well, this sort of is what was being described for this style of deposit. I have no templates or no recipe or simple answer. Good fieldwork by well-trained geologists is most essential. Thank you. Is that it, Diego?
Yes, there is a question more. Harold Samoya, please open your microphone.
Yes, good afternoon. Thanks for your presentation. My question is, could we see the characteristics of porphyry or an epithermal transition in breccias? We can zone these characteristics like the mineralization or alteration in breccias?
There are lots of breccias. There are primary volcaniclastic fragmental rocks, breccias, those related to hydrothermal eruptions, ferromagnetic eruptions, fault movement, et cetera, So we have to first be very descriptive with fragmental rocks to try and figure out how they formed, how they're related to potential mineralization. I'm not sure that, again, I can generalize about breccias, but I'm going to have one example from Yanacocha later in the second lecture on transition from epithermal to porphyry. So let's wait until we get to that. We'll show there a fairly classic transition from base of lithocap into the stockwork veins. Okay. So is that it, Diego?
Yes. Yeah. One question more. Zahira Martinez.
Yes.
Open your microphone.
Okay. Good afternoon, Dr. Jeffrey. It's nice to.
Hey there. Good to hear you.
Yes. Can you hear me?
Yep.
Okay. So my question is, what types of rocks are most likely to be called lithocaps beside tuffs? I mean, is there any special things about the grain size or something?
Well, grain size is a good point. I mean, we can get a variety of mechanisms to form variations in grain size. If we have grain size that is too small, for example, shales or ash tuffs, those can be easily, shales are very impermeable, of course, aquatards, very fine-grained tuffs, very quickly alter. A lot of glass, they alter very quickly. Tuffs, I should say, lapilli tuffs, where you have some lithic class, etc. But it all depends. I'm not sure that I would want to generalize about grain size, but it all depends on how permeable a horizon is to start with, and how permeable it continues to be on alteration. And it's not easy to generalize. It may vary case by case, but certainly sedimentary horizons, whether they're volcaniclastic or otherwise, can be relatively permeable. But they can also be aquatards, so case by case. I'm going to show one example here from Ecuador in the next section, and just highlight that the nature of permeability of lithologies. But it's a good question that I can't exactly answer in a general way. Okay.
There is one more question.
Yeah. Before we go on.
Okay. Can you please explain again the relationship between the residual silica with the creamy silica?
Yeah, residual silica is silica residual due to lixiviation. If we have a rhyolite, it contains about 71% silica, right? And aluminum, sodium, potassium, calcium, making up feldspars, plagioclase, potassium feldspar, some quartz phenocryst, mafic minerals, etc., biotite, hornblende. But if we have a pH 1 solution, it will dissolve everything in the rock except for silica, because silica in solution is silicic acid, H4SiO4. And as a result, acid conditions does not increase the solubility of silica. So the silica that was originally 71%, it can rise, as I showed, up to maybe 97% once we remove all the aluminum, sodium, potassium, calcium, iron, magnesium from the rock, it's a residue. By contrast, if we have a very rapidly cooling liquid that's bringing in copper and gold, it's cooling so fast that it doesn't precipitate quartz in some type of a structure, a permeable structure. Eventually, it will reach amorphous silica solubility, and then we start to deposit amorphous silica colloids, colloidal silica, silica colloidal. And that's why sometimes the high grades gold is associated with colloidal silica that's depositing from solution, whereas silica residual was always there. It's the remnant. It's what's left behind after lixiviation, whereas silica colloidal is added by the mineralizing fluid. I have some slides discussing those details, but again, given the 3 hours to cover all this material, I had to take out those details. So one is the residual, the other is the addition. Okay, we'll have some more examples of them in a moment, so let's move on to those. Now, these are zones that I've worked on with lithocaps in the Andes. They're not continuous lithocaps, but these pink or orange zones have lithocaps in the areas, even though they may not be labeled here with dots. Here's a close-up in central Chile of some more lithocaps, a lot of them with recently discovered deposits, Valeriano, porphyry beneath, Pascua hosting lithocap, El Indio hosted by a very small lithocap, Filo de Sol, porphyry with a lithocap overprint of the porphyry, etc. Of course, in Ecuador, we're going to take a look at one example, Quimsicocha, now called Loma Larga. Yanacocha, we've already discussed it briefly. We're going to come back to another example later on. We're going to look at Arantani and Cañuiri in southern Peru. And we've already mentioned Licoipa. I'm going to use Licoipa again to discuss how that was important. Licoipa's characteristics were important in the discovery of Salares Norte deposit below a steam heated cap here. So back to Licoipa. As we saw, the first discovery was Ladera Ferrion, a dacite dome outcropping here with very nice residual quartz. The dacite porphyry, we can see the vuggy texture after phenocrystallase due to lixiviation. And then this this very friable, porous horizon of siliceous rock with alunite and kaolinite overlying Coipa Norte. And at Puren, there was a large area of this steam-heated alteration. So initially, two companies drilled on this steam-heated alteration. They drilled 12 holes, but they weren't able to find any mineralization at depth below the steam-heated alteration. But Placer Dome continued to explore in this area, and they eventually found another target, Puren Norte, using geophysics and geochemistry. And they eventually drilled through the steam-heated blanket about 40, 50, 60, 70 meters thick, steam-heated blanket of kaolinite in blue, and they drilled into a quartz silver gold ore body with halo of illite. Here was the silver greater than 65 grams per ton, with gold less than 1 gram per ton. This was the 100 to 1 silver gold ore body. And here you can see that Puren has gone into production. And here's that beautiful steam heated blanket of kilnite. And the reason that it has a flat base is because the groundwater table would have been flat. And so the H2S in the low temperature vapors rose up, condensed, and oxidized in the zona vadosa. And those condensates caused the kilnite alteration, pH 2 to 3. And as the condensates flowed down to the paleo groundwater table and flowed off, the silica-bearing condensates then flowed off along the paleo groundwater table, caused silicification. And this was low temperature silicification, so it was opal. And we can see here the silica conchoidal nature of opal, and we can actually see this crystal tuff texture of this horizon that's been silicified with opal. Okay. Well, some of my colleagues in Goldfields came here to look at this deposit, and they understood that basically there's very little. Here we had only less than 3 grams per ton silver, and essentially no anomaly in gold, just a couple ppb. So they realized that you don't have to have a metal anomaly in the steam heated zone because they're typically barren. So here was La Coipa mine with Puren to the northeast, and Goldfields was exploring this area about 75 kilometers to the northeast of La Coipa. Large amount of steam heated alteration. And they focused on 4 targets. And the lowest elevation, easiest to get to, was Pircas, and then also Piedra Prada and Piedra. And these 2 were discounted after field work, 1 or 2 drill holes here, but Pircas was drilled, and there was some reasonable mineralization, but it was small. Finally got to the Solares Norte, over 4,500 meters elevation, no drill roads up here. And that was the deposit that was eventually defined. As I say, they focused on spectral anomalies in this corridor and focused on 4 of the spectral anomalies for follow-up work. This is Solares Norte. This is a blending of aster with Landsat, because this blue is opal and aster doesn't have the bands that show anything to do with silica. Rather, you can get that by examining Landsat images. So blending the 2 together, the kilnite and the alunite were defined from aster, shortwave infrared spectra, and the opaline blue, the amorphous silica or opaline material from Landsat. Defined, here's the dacite dome, and this red triangle is where the deposit was eventually found blind at depth on the margin of the dome. Here's the dacite dome. We see all the steam heated kilnite alteration in white. There's breccia principal. We'll come back to that in a moment. And there were anomalous trace elements, some arsenic, antimony, lead, bismuth, mercury, anomalous. These are actually talus fines, not soil. But rock chips, all less than 35 ppb gold. And in in the talus fines, less than 24 ppb gold, except for one sample with 0.6 ppb gold. And that was in a breccia fragment within breccia principal. So most companies would have looked at these anomalies and said, well, you know, there's no gold anomaly. We're not going to drill this. But Goldfields realized that, you know, this was a large altered system. They also had a margin of a magnetic low. They had coincident resistor indicating siliceous zone at depth, a high resistivity zone. And they'd already tested this through their study at Pircas, which was mineralized but small. And breccia principal was recognized to be a phreatomagmatic breccia. You could see the wispy or the juvenile textures. So you know that this type of phreatomagmatic dome is, or body, has a great depth extension, possible zone of cross-cutting permeability. So that led to them drilling 2 RC holes here. The first RC hole was lost at 85 meters. The second RC hole at 180 meters below the surface hit the top of mineralization, cut almost 100 meters or 1.5 grams. That was the discovery hole. Above 180 meters, it was all basically unmineralized steam heated alteration. So this is a cross-section courtesy of Nate Brewer, the exploration manager for Goldfields. And here we see in purple the breccia, the diatreme breccia diatrema, cutting through to the surface. And we have a variety of alteration types here. We have quartz alunite and kilnite dicite. These are the hypogene zones of advanced argillic alteration. And this is where we find brecciated rock and silica gel, this colloidal silica gel, along with vuggy gold, visible gold, so high grades, where the colloidal silica was cementing the breccia fragments. And then the second type of alteration is a steam heated alteration. A variety of zones of steam heated alteration, low temperature, kilnite, a bit of alunite, as well as opaline silica. And we could see opaline silica down to about 130 meters elevations, at least 130 meters below Paley surface, 150 meters below Paley surface. And then there was a third style of alteration. That was supergene oxidation of pyrite. And so we get this supergene oxidation blanket, and where it's in the area of the permeable diatreme, that supergene oxidation actually penetrated deeper. So 3 types of alteration. Hypogene advanced argillic alteration. Here we can see the quartz alunite and residual quartz, fragmental, steam heated blanket of alteration, alunite, kilnite, and then late overprint, post-mineral overprint of supergene. And they all have a different morphology, a different mineralogy, textures, etc. So these have to be mapped. And the first thing to realize is these are all possible alteration types here. So it's good to go to a place like Puren and recognize what is present in the district before you go and start looking at a greenfields opportunity. And these were the 3 different sources of acidity that I talked about. SO2 disproportionation, low pH. H2S oxidation above groundwater table, pH 2.5. And then pyrite oxidation, supergene, phosphoric acid, that can also give low pHs, but not silica residual. Another diagram, courtesy of Nate Brewer, very sharp top to mineralization that was controlled by the top of the hydrothermal system, only steam heated alteration at a higher level. Two ore bodies, Brecha Principal and Agua Amarga, very flat lying, particularly in this case, a lithocap controlled to Agua Amarga, but here largely the high grades in that Brecha Principal, that diatreme breccia, actually probably in through here. And right, here is the first drill core hole drilled into Brecha Principal. At shallow levels, there is the residual quartz fractured. We even see some silica colloidal sealing the breccias, but this interval contained only 50 ppb gold. Whereas this interval in the same drill hole, the same brecciated rock, the same silica residual, or the same silica colloidal cementing the breccias, but here there's 980 grams per ton gold in this sample, 100 meters below this particular level. So this sample was from somewhere up here. This sample was down in the high-grade part of the ore body. So a very sharp top to the mineralizing fluids, mineralizing liquids. Very important to note. Any questions about those particular examples before I go on and start looking at a few more case histories?
There is a question by Aldo Bendesu. He asked, regarding pathfinders, molybdenum can be transported by both vapor and hypersaline phases from deeper porphyry copper sources. Given this, can molybdenum be effectively used to vector towards disseminated epithermal gold ore bodies and porphyry copper deposits? I mean, into the lithocap environment.
Most molybdenum is transported in the liquid phase related to porphyry copper moly deposits. There are some local, very local molybdenum anomalies. They're called molybdenum blue. It's a molybdenum oxide that concentrates right around the high temperature fumaroles. At Satsuma Ujima, we collected one fumarole, 880 degree temperatures, and there was a halo, blue halo around that fumarole of molybdenum oxide. So yes, if you collected a sample of that, you would know that there had been, and you could see the lixiviated rock, you would say, yes, we're very proximal. So if in rock that is otherwise sterile, you see some molybdenum anomalies, it could be molybdenum transported, but it's very, very proximal to the high temperature halos. Unfortunately, I don't have a photograph now. I just made myself a note. I'm going to try to get one for future questions like this. So if you do find any molybdenum in sterile lithocaps, it might suggest that you're very close to a fumarole vent, or there was a little bit of mobility of that molybdenum. Certainly very, very, very proximal. Okay.
There are no more questions, Dr.
Okay, good. We'll go on to the case studies. Here we're going to Ecuador. I hope that there's some people from the two student chapters in Quito, and this is in southern Ecuador. At the time of discovery, it was called Quimsacocha, although the name has been changed to Loma Larga now. It's about 4,000 meters elevation through here with these ribs, structurally controlled ribs of residual quartz and quartz alunite, very resistant. Low elevation, there's a stream down here at 3,600 meters with quartz veins with enargite and gold, which is important, 3,600 meters down in the river valley. But up here, about 3,800 meters elevation. This is the history. British Geological Survey collected samples for porphyry copper exploration, 1970s. Kojema, a French company, got these samples, analyzed them for gold, recognized there were some anomalies in this area, and found this alteration. They drilled 10 holes, about 180 meter deep holes, but they're a uranium exploration company, and they didn't really understand what they had. So they joint ventured with Newmont. Newmont sent geologists from northern Peru, from Yanacocha, and Newmont started calling this area Yanacocha Norte. Why? Because they thought that they were going to find another very shallow series of ore bodies within 50 or 100 meters deep that could be open strip mined, that would be supergene oxidized, etc. That is why they drilled 82 drill holes, 7,600 meters total, average depth 93 meters inclined. Why? Because any ore body that they wanted to find, they thought had to be in the shallow, less than 100 meter deep zone to be able to open strip mine. Well, they didn't find what they were looking for, and so they dropped the JV, but they did have the best intersection, 2 meters of 83 grams. Subsequently, IAMGOLD JV'd on this property, and the exploration manager was a structural geologist. He saw this narrow interval of high grade, and he said, there must be structural control to high grades. So when they started to drill in 2002, their average drill depth, 330 meters. On drill hole 40, they found 100 meters of 9.5 grams gold, structurally controlled feeder zone. And by 2005, they defined almost 3 million ounce gold resource, which is still waiting for regulatory approval. Well, this is a map, geologic map from Newmont mapping days. And we can see a 4 kilometer diameter circular cauldron here of structure with cut by a diatreme breccia in blue, and then intruded by these porphyry dacite domes. Now, interesting breccia diatreme because it contains fragments with porphyry copper lithics, with up to 0.2 or average 0.2% copper in those porphyry copper fragments. And then we also see all of these radial lava flows of andesites. Andesites with a variety of interbedded tuffs. We'll next look at the alteration, same area. There's the diatreme breccia. And here we have in blues, unfortunately blues rather than reds, blues are vuggy or massive quartz. The purple is quartz alunite. So these structurally controlled ridges are quartz alunite and locally quartz, massive silica, but with relatively low grades of gold. This is a very important cross-section, coming back to Zahira's question. And we see the andesitic lavas. The horizons of residual quartz are not following the lavas. They're following lapilli tuffs, tuffas gruesas, lapillis, and these lapilli tuffs were obviously permeable. I think, yeah. Here is a view of one drill hole, 230 meters deep. Here through this lapilli tuff, showing the lapillis here are open. They are pumices. So this lapilli tuff was a pyroclastic flow, unwelded, because the pumices still are not compressed to fiamme. And this horizon was permeable. In fact, multiple horizons of tuff. Newmont, their average depth of drilling went through only the upper horizons of tuff that were largely sterile. There was some mineralization, including 2 meters of 83 grams along some structure, but largely sterile, and that is why Newmont decided to leave. Subsequently, IAMGOLD came in and started drilling 300-meter deep holes, we can see here, intersecting these deeper horizon. Now, as we know, as I mentioned earlier, there's never a rootless lithocap. All lithocaps have feeder zones. So the question is, where's the feeder zone? And so that's what took IAMGOLD 40 drill holes. Their drill holes started with number 83 after the 82 Newmont holes. They drilled until they discovered high grade in drill hole number 122, the 40th drill hole. Some of the early drill holes, like 95, 102, 103, 110, they were only hitting this deep horizon of residual quartz, silicification, residual quartz, and with halos in yellow of kelnite illite. And you can see in these two drill holes, there's only kelnite illite halos out to smectite. We'll talk about illite smectite in a moment. But here in 102, in the hanging wall, there's dicite proflite, alunite, before moving out to kelnite illite and smectite. The footwall is still kelnite illite. And then hole 103, there's proflite dicite in both hanging and footwalls. And as I'll discuss in a moment, proflite and dicite are stable at higher temperatures than kelnite. And so, of course, the indication is for higher temperatures to the south. So which direction should we drill? Well, these 95, 110, they also have only 1 gram gold. 1 gram gold, 0.1% copper at 200 meters depth. This is not going to be economic. Again, drill hole 102, 1.3 ppm grams per ton gold. Still not really a reasonable grade. 103, we're starting to see higher grades, 4 grams gold still, and 3% copper, but still, not really high enough grades. So eventually they drill tested the target here of higher temperatures to the south. These, as I mentioned, halloysite kelnite or aluminosilicates indicate lower temperatures, less than 200 degrees, whereas dicite and then porphyrite indicate higher temperatures, as does zinnite and topaz, the fluorine-bearing minerals, at least 250 degrees. So obviously this should be our target. And this was drill hole, the discovery hole 122. with 100 meters of almost 10 grams gold, basically intersecting the feeder zone. Because as I mentioned earlier, highest grades are always in the feeder zones. So if we're finding low grades in the lithocap, we have to find a way to reach this structurally controlled feeder zone, whether it's structure or dome margin or diatreme, et cetera, et cetera. That is where we can expect to find the highest grades. So I've promised this, we already looked briefly at the lumisilicates, but this diagram shows the temperature stabilities of minerals. As I mentioned, alunite has no temperature stability as a mineral, but potassium-rich alunite usually is seen to be lower temperatures, sodium-rich alunite higher temperatures. These are the acid-stable minerals: alunite, halloysite, keelnite, dickite, porphyrite, diaspore, zunite, etc. In contrast to the near-neutral pH stable minerals such as smectite, illite smectite, chlorite smectite, illite muscovite chlorite. They all, though, have temperature stabilities, and so they're going to be zoned. The highest temperature minerals closest to the high temperature feeder zone, the lower temperature minerals on the margins. So this is why we should try to target these temperature sensitive minerals. And most of these minerals have hydroxyl or sulfate bonds, and therefore they can be identified on shortwave infrared, Teraspec or PIMA. I'm not going to go into all the details here, but these different minerals do help to characterize the different environments of high sulfidation, intermediate sulfidation veins, or low sulfidation veins. With the volcanic arcs, those deposits tending to be deeper and associated with more high temperature minerals versus our lower temperature, shallower and lower temperature rift related deposits. And amorphous silica, if we have a lot of amorphous silica, some of these minerals, dickite and porphyrite, can actually be stable at lower temperatures, something to keep in mind. So back to the Kimzicocha Loma Larga cross section. This is the discovery hole, gold, and lower grade, 2 grams gold. It was this high grade to result in sufficient high grades to increase the average grade of the deposit. 2 grams average grade of sulfides at 150 meters depth would not have been economic to mine by underground, which is the plan here. And then we see the upper lithocap, largely sterile. Locally, some grades, probably along structures, but most of that lithocap related to the shallow level of permeable tuff above the mineralization horizon, just like we saw at Salares Norte. There's a lower zone of mineralization and a shallower zone of sterile alteration. So keep that always in mind. You may have a shallow, depending on the level of erosion, you might have a shallow sterile zone. Focus on the feeder zones, defining where the feeder zones are. If you can find a feeder zone and it also has low grade, you probably can kill the project and move on to another. Well, I mentioned earlier that there was a quartz vein with enargite and gold in the valley about 1 or 2 kilometers, about 1 kilometer away at lower elevation. 2020 hindsight, that was the horizon of mineralization. That was telling us something about how deep we should be drilling. Again, hindsight, as we say in English, is 2020. We all can say, well, we should have recognized this in the past. And you can see very very narrow horizon of mineralization of 2 to 10 to 20 grams mineralization in this residual quartz zone with quartz alunite sterile at higher elevation. Loma Larga eventually had a 3.3 million ounce resource, but now the mineable resource, 2.2 million ounces. The reserves were 14 million tons of almost 5 grams gold. And that's because of the feeder zone, with about 0.3% copper as enargite. And make sure you drill deep enough to get through what might be multiple permeable horizons, permeable lithocaps. And there you have to simply map the local stratigraphy to know what are the possible lithocap horizons. Okay. I'll just run through one more example. District in southern Peru. And here, Yanacocha was discovered in mid-1990s, went into production 1993. Parina, 1996, discovered. Alto Chicama, discovered in 2000. But in about 1990, just after discovery of Parina, Arntani Company, Guerra del Castillo, asked his chief geologist, Dante Loaiza, why can't we have this style of deposit in southern Peru? Because so far, of course, southern Peru was known for its silver veins, like Orcapampa, Arcata, etc. And that's why, most major companies were not interested, like Newmont, like Barrick, etc. They were not interested in silver deposits, silver veins. So they were not working in southern Peru. But in 1997, Arntani discovered a small lithocap-hosted high sulfidation deposit, and that led to them exploring in the district to find a larger deposit in 2000. I'll just discuss those now, because that was important to then bring in Buenaventura and Goldfields back to or into southern Peru, and they eventually found an even larger deposit at Cañueri. And subsequently, discovered in Moquegua, Puno, Cusco, Ayacucho, Apurimac, these styles of deposits. Some not so large, 500,000 ounces, but up to 1.5, 2 million ounces. In total, 400 tons of gold discovered since 2002. This is the western Tucari district. One reason why it wasn't well known was because it was very high elevation, 5,240 meters at the top here. And this is a presentation made in Perth, Australia in 2004 by Dante Loaiza et al. And this gold enargite district was discovered in an area of abandoned lead, zinc, silver veins. Well, what were those silver lead, zinc veins? They were intermediate sulfidation veins, just like I showed at adjacent to Lepanto lithocap in the Philippines. There were intermediate sulfidation veins on the margin of the lithocap. Here is some of the discovery crew and the crew drilling out with Jorge. Here's Dante Loaiza, who led the group, and Jorge Vareda, who drilled out Arantani, he came from Newmont, did an excellent job. Unfortunately, he passed away at an early age. Here's some work that Alvaro Costa did, Landsat, just identifying the extent of this very large alteration zone from Landsat. And Cacachara was the original lead zinc silver vein. Right through here, there was another Pivico nearby, and that's where Arantani company came and started looking around and eventually found a lithocap at Santa Rosa. And based on that, they started exploring this district and finally identified Tucari. Both of these being lithocap-hosted high sulfidation deposits. Santa Rosa, discovered in 1997, smaller, 0.4 million ounces, but that led to the discovery of the larger, greater than 2 million ounce deposit at Tucari. So it was really these intermediate sulfidation veins, small, that led to discovery of the lithocaps and the deposits in this district. So one has to be familiar with all parts of this model, the porphyry copper system, which includes lithocaps, includes high sulfidation deposits, includes epithermal intermediate sulfidation deposits, polymetallic. Well, here is Tucari, looking to the north, the southern slope, this scree zone with 1.5 grams per ton gold in the scree coming off residual quartz. And we'll look at a cross-section through the deposit, roughly north-south, northwest, southeast. And here we see the Barroso andesite volcanics, which many people had explored, but didn't find much interest in southern Peru. What was recognized, however, here is that it was necessary for later dacite domes to be intruding the Barroso volcanic rocks to result in mineralization. And that was mapped out by Wolfgang Morsche, a volcanologist in this area. And now I'll show you the alteration and mineralization. You can see that dacite dome essentially was the focus of the deposit. The residual quartz locally with massive silicic alteration, but residual quartz, both buggy and granular, with a halo of quartz alunite in orange. And that basically, that quartz alunite halo marked the margins of the oxide gold ore body, 0.25 grams, whereas the average grade was over 1 gram, 1.2, 1.4 grams grade. But their cutoff was below 0.25 grams. Sometimes down when the gold price was up, their cutoff was as low as 0.15 grams per ton gold. They could still make a profit by moving this rock, oxidized rock, to the heap leach pad. Here is Jorge Barreda looking at core from drill core at 4,980 meters. This is basically the base of mineralization. Mineralization starting at over 5,200 meters. And this discovery of Tucari awakened interest. First it was Santa Rosa that led to Tucari discovery, but then discovery of Tucari reawakened the interest by the juniors in this area. And that's when Buenaventura already had been in the area, but Goldfields came into the area and did a JV, joint venture, Canteras del Halazago in green, and they joint ventured. It was called Chucapaca, although Goldfields had other land around the margin. And the joint venture group, they had, Goldfields had attended our presentation in Perth in 2004. And so they knew the importance of these dacite domes. And here's a Chuquipaca, the dacite dome with lithocap alteration of residual quartz and andesite, quartz alunite, some 0.5 gram grades. And eventually, Goldfields decided, well, they drilled 12 holes here, but decided to turn the JV over to Buenaventura. Buenaventura was interested because of the intrusion center district into these sediments. These are all Jurassic sediments into here. Close up of those sediments, there was what thought to be a sulfide oxidation zone, a Gaussian. Here we can see those sediments. So Buenaventura was interested in the possibility of carbonate replacement mineralization related to this dome centered district. Well, Buenaventura didn't find any carbonate replacement deposits. They drilled on this Gaussian, but it turns out it's not a Gaussian. Gaussian is defined as sulfide oxidation. This is actually a pseudo-Gaussian of oxidation of iron carbonates, anchorite. And they drilled 6 holes. The first 5 holes didn't report any zinc or any gold. The 6th and last hole, no zinc, but intersected over 120 meters of about 2 grams gold. So they drilled a total of 25 holes, and then Goldfields backed into the JV and operated it, drilled it out, and by 2011 had defined 230 tons of gold. But this gold mineralization is related to a diatreme about 4 kilometers on the margins of this dome complex, low-grade lithocap-hosted dome complex. Here you can see the juvenile class in the dome here at Cañueri. And this diatreme-related mineralization is not high sulfidation. This is actually diatreme-hosted tentite chalcopyrite sphalerite. This is intermediate sulfidation mineralization on the margins of the lithocap. Almost 9 million ounces gold equivalent. As I mentioned, hosted by the diatreme on the margin of the dome, the quartz alunite lithocap of the dome. So this was a case where one actually had to look on the margins, think laterally, but also move laterally. So both figuratively and literally, thinking laterally. Intermediate sulfidation system on the margin of a low-grade lithocap. So before the last questions, before the last section, anybody have questions there? Diego?
There are no questions, Doctor.
Okay, good. Well, I will finish this up and then we'll move to the second and shorter lecture. This is now the transition from lithocap to porphyry. And we're back at Yanacocha. Yanacocha, at least a dozen ore bodies, most related to domes in this area. Yanacocha Norte, a huge deposit, 4 deposits that coalesced into a super pit. The first deposit, mine, Maki, Chequicocha, the deposit underground, sulfide, related to this dome here. San Jose produced about 4 million ounces of gold. And we're now going to take a look at the margin of the San Jose lithocap-hosted deposit, but we're going to walk down into the Kupfertal Valley. And Kupfertal in Deutsch is Copper Valley. And one of the geologists working here on this assessment was German. So that's how it got the name Valley of Copper, Kupfertal. Well, here we're on the edge of San Jose pit, 4 million ounces of gold hosted by residual quartz with quartz alunite halo. Here, this is quartz alunite, and we start to walk almost 300 meters down into this valley. And halfway down the valley, we start to find this pyrophyllite replacement of the quartz alunite. This was originally called silica patchy at Yanacocha, but it's not patches of silica, it's patches of pyrophyllite or alunite or dickite replacing the rock. We move further down the valley, we'll see more patches, even Gusano, where the patches of pyrophyllite have started to coalesce to form a wormy Gusano texture. And Newmont geologists drilled, put 5 drill holes in this area. The third drill hole is shown here. At depth, there are veins of porphyry copper, quartz veins with muscovite, but then crossing a fault zone through here, and we're up into pyrophyllite, kaolinite, pyrophyllite alunite, and we see at depth, of course, also more of this patchy texture, patchy pyrophyllite replacing quartz alunite. At the base of the valley, veins of quartz veins related to porphyry. This is some of this porphyry stockwork veining in drill hole 3, but also white mica overprint of the veins and pyrophyllite and dickite. And even if we look carefully, we might be able to see some patchy texture in some of the outcrop in the valley. Why do we get this pyrophyllite, patchy pyrophyllite? It's very simply due to cooling. At higher temperatures, we have white mica, muscovite, stable, maybe with andalusite, at lower temperature than Cape Feldspar, but cooling of the muscovite results in muscovite to pyrophyllite stability. And that's very simply why we see this zonation. At the lower temperature roots of higher temperature roots of a lithocap, about 300 degrees, is where this transition of white mica to pyrophyllite takes place, and then to dickite at lower temperatures. So here we see there was the location of drill hole 3 in Kupfertal Valley. We see the patchy textures at shallow levels of pyrophyllite replacing, and then down to these stockworks of quartz veins in the porphyry, the Kupfertal porphyry. And the porphyry, Kupfertal porphyry, biotite of the Kupfertal porphyry dated at 10.73 million years by argon-argon. Alunite at San Jose, 10.73. At Corrimayo, lithocap hosted deposit, alunite dated at 10.76, but both of these completely overlapping with the porphyry-related biotite. So these lithocaps formed at the same time as the deeper porphyry, possibly, almost probably, in my opinion, these lithocaps formed on the shoulders of the deep porphyry system. Why? Because over the top of the porphyry, the temperatures were too hot. They were pyrophyllite stable, too hot to result in low temperatures of low enough to cause lixiviation, cause residual quartz. They flowed out along the hydraulic gradients to the margins where the lithocaps formed on the margins of the deep porphyry. So these are the lithocaps, mineralized lithocaps, related to the underlying deeper Kuffertal porphyry. That's the argument, and that's something to keep in mind if you're looking at lithocaps, whether they're mineralized or barren. If you're looking for the deeper porphyries, don't drill directly below the lithocaps, because they may be on the margins of the deeper porphyry. Finally, ending up this lecture, you should all have a copy of these lecture notes, but if anybody doesn't, please contact Zucker. I sent out these PDF of both lecture notes. This shows the 5 relationships of advanced argillic alteration. As we already discussed, we saw the bubbling mud pools, steam-heated acid sulfate. That forms a blanket above the paleo groundwater table. Another type that we didn't discuss is also steam-heated, but CO2 rich, carbonic acid rich, that forms clay halos to our epithermal gold deposits, gold-silver veins. The main alteration we discussed that forms the lithocaps are the condensation of the vapors, the magmatic hypogene vapors, and formation of acid sulfate chloride, pH less than 2, pH 1 solutions that cause lixiviation, residual quartz, quartz alunite halos, quartz kaolinite halos. Also, perovskite is by definition advanced argillic, but in this case, it's not formed by a vapor condensate. It's actually formed simply by cooling of white mica into perovskite stability, or even into dickite stability. So cooling itself can be a cause of formation of advanced argillic minerals. And finally, of course, is our supergene oxidation environment. Post-hydrothermal oxidation of pyrite, and we'll get also low temperature advanced argillic alteration minerals. But very importantly, it's important to maintain the mineralogies, describe the minerals, but also their textures and their morphologies to be able to identify which of these 5 different environments, because these 5 different environments all have different spatial relationships to potential epithermal and porphyry mineralization. And they're essential to understand as we explore for both lithocap-related epithermal as well as deeper porphyry. So I think, yes, that's the end of the first lecture. As I said, the second lecture is shorter. I'll just talk about that transition into the porphyry environment already introduced. But before we do, are there any questions, Diego?
No, teacher, there are no questions.
Okay, none. Well, I had to go fill my water glass and also change to the other set of slides. So, yeah, please.
Oscar Daniel, please open your microphone.
Who's going to ask, Oscar?
Yes,
Oh, sorry, can you hear me?
Yes.
Okay, thanks. Well, I was saying that thank you for this interesting lecture. It was awesome to know a little bit more about lithocaps and its association with porphyry copper deposits. And well, my question is related with something more petrological, and it is if there is any possibility to take advantage of the information from magmas that could be fertile to produce porphyry copper deposits. Do you know if there exists any advantage, for example, like to analyze if a magma is an oxidized magma or the pH state of the magma in order to see if this magma could be fertile to produce this kind of deposits, or maybe nowadays we are not like taking advantage of this information.
Yeah, that's a good point, because there were maybe 15 years ago or more people talking about fertile magmas. I call them magic magmas. People thought there were some magic magmas that that had more metals in them, or somehow were better able to form porphyry deposits. But extremely careful work in Europe by a variety of people like Andreas Audete in Germany, and particularly Massimo Chiaria in Switzerland, who's just is receiving next month the SEG Silver Award for his research over the last 10 years. He's had several papers, 5 or 6 in the last 10 years, that basically demonstrate that any magma can form a porphyry copper deposit. It depends on tectonics. It depends on size of magma chambers, life of magma chambers, cooling pathways, etc. But there are no special magmas. Now, I just read this stuff. I don't know. I don't really understand it. So I'm not going to say any more about it, except that his arguments fit my ideas, that there are no magic magmas. There are no, we cannot look at the petrology of a magma to say that this is going to form a porphyry deposit better than another. Of course, that doesn't mean that petrological studies, dating studies, etc., are worthless. By no means. We need to know those details on a district basis. But in the end, it comes down to much broader tectonic considerations. And as the saying goes, if you're looking for elephants, go to elephant country. Even though you might be 50, 100 kilometers from elephant country, large porphyry deposits, it's still relatively, that would be considered fertile, the right tectonic settings, as opposed to looking for the magic magma. I hope I don't disappoint you too much, but please read some papers by Massimo Chiaria. He has 1 or 2 papers in economic geology and a few other papers in Nature publications. And I'll try to look for one particular good one, most recent one, and send to Sukar so he can distribute those along with a couple of our more recent papers, just to show you where our thinking is going. Maybe we're not right, but this is at least what we're thinking. Okay?
Okay, thanks, Mr. Jeffrey.
Yeah, anything else?
Yes, Miguel Ponce asked, is it possible to have non-economical porphyries below mineralized lithocaps?
Oh, yeah. I don't know of any. That's a good question. I don't know of any. There certainly are non-economic lithocaps over mineralized porphyries. So one time people said, well, is the size of the high sulfidation deposit related to the size and grade of the porphyry? Definitely not, because we know of look at Valeriano. Largely there might be 500,000 ounces of gold in part of that lithocap, but now ATEX is drilling out the Valeriano porphyry, which was discovered when Hochschild did not find any significant mineralization in the lithocap, but then they bottomed into the top of a porphyry. That was a really nice discovery, and I discussed that discovery in my one day presentations rather than the 3-hour presentations. So Yes, now that I have my slides turned off, I see some of the chat messages. I see Aldo's question about pathfinders and molybdenum. I'll try to find the photograph. Unfortunately, those are all I did that work back in 1992, when all photos were slides. So I've got some good photographs of moly blue around high temperature fumaroles, but they're all as slides. They've not been scanned yet as digital images. But I'll look for those and try to send it. Okay, so how about if Zahira has another question?
Yes, Zahira Martinez, please.
There's still another lecture to come. What's up?
Okay, my question is there any textural difference between magmatic hydrothermal cooling pyrophyllite and that was from the acidic environment? Yeah, good question. And see, I often say good questions when I don't know the answer. Certainly, there are potentially two styles of pyrophyllite. You can get aluminosilicates in that very acidic environment on the margins. I don't know, except that, well, let's just consider, the thought process. Pyrophyllite that's formed from a cooling white mica fluid, well, commonly will be intergrown with white mica. That's what we see at El Salvador. And because when you look at it by SEM, and everybody doesn't have an SEM, but when you look at that, you see the ingrown. In contrast, within the roots of the lithocap, you would see pyrophyllite and dicite and alunite. So if you are able to look at least thin section images, you might see differences. Look for the white mica association. And of course, you may also see that in thin section or in hand lens or in shortwave infrared. You might see a lot of pyrophyllite and white mica, illite, versus cases where you see pyrophyllite, alunite, and dicite, perhaps, which would be possibly indicating more acidic solutions. So that would be the things to look for, I would say. Yeah. Thank you.
Okay. So, I'll ask somebody. I'll ask somebody about non-economic porphyries underneath underneath mineralized lithocaps. Maybe Sukar can do a screenshot or something, or a save. Hopefully, Google allows the chat questions to be saved, because once you turn off the this session, you'll definitely lose everything. Let me. I've got to turn off this to start the next. Yeah, two. Let's see. Yeah, there's the second one. Let me go get another glass of water, please. Okay, I realize that Uni advertised this as 2 to 5 Peru time, and I'm not going to finish this next set of lectures by 5 o'clock, but I will go through until the end. I'll go fairly quickly through porphyry features because it's not the main topic here, to be able to look at that transition, lithocap to the tops of porphyries. And so if anybody has to leave at 5, please, you can depart, but I will continue until these slides are finished, or at least until there's still one other person listening, maybe Sukar and Danielle, or not, sorry, and and Sergio, or Diego, sorry. This is just my general introduction. Already mentioned porphyry copper deposits, over 70% of the world's copper, half the world's moly, maybe 20%. These are the systems, including epithermal. 20% or so of the gold, and a lot of the rhenium and indium, and variable amounts of the silver, lead, etc., selenium, bismuth, with Mexico and Peru accounting for most of the world's epithermal silver, and that's probably providing well over a quarter, 30% of the world's silver. And we're going to be needing more of it. Even though we're improving our recycling, even by 2050, people think that we'll still not get to more than 30% recycling of copper. And the demand for copper could double. So that means basically the mined demand will almost double. Therefore, we need well-trained, experienced, competent geologists to find the next porphyries. So, discuss a little bit about general topics. We've already seen this diagram. I'll zoom through it. We start off with this critical fluid. Now that we're drilling below many porphyries, far southeast, Bingham, that'll show a bit later, and many others, we actually see these critical behavior inclusions there. And Andreas Odete has studied many of these critical inclusions. So if anybody's interested in that, they should look at it. And we now recognize that the way that you get a high salinity, hypersaline liquid of 50, 60, 70% is not from direct exsolution from the magma, but from removing 80, 90% of the water from the liquid as vapor. Henley and McNabb recognized that in 1978. And as we already said, the vapor ascends. Some of it discharges as degassing volcanoes, but part of the vapor condenses. At Satsuma-Bijima, about 1/3 of the vapor that rises condenses. 2/3 of the vapors discharge from the fumaroles. But we were able to estimate the flux from the volcano because we had that island condensate flowing off to the ocean. We could measure that flux as well. So there's no question. Lithocaps are intimately linked to the porphyry copper environment. When we don't see lithocaps, it simply means that the lithocaps have been eroded, not that they were never formed. Of course, we may have relatively small lithocaps if we didn't condense very much of that vapor, but overall, there's always going to be lithocap there. That should just be taken as a given. Of course, people in Southwest US took a long time to accept that, but even now, we're finding lithocaps in Southwest US, and some of them related to porphyries. So we discussed the lithocap and epithermal environment before, but now we're going to take a look at that transition to the porphyry. I often also consider the epithermal veins adjacent to lithocaps, but again, that is when I have another hour or so. So this time we're just going to consider this transition. This is a compilation by Don Singer. Depth to the average depth at the tops of, say, porphyry copper deposits, about 1.5 kilometers, but some as deep as maybe 4. Copper moly, as I mentioned earlier, they may be 2.5 kilometers, they're somewhat deeper. And gold-rich porphyry is somewhat shallower. But this is where I would take exception at, because Don Singer only summarized what was in the literature. And there are some errors in the literature about how deep some porphyry copper gold deposits are formed. Well, many lithocaps form 600, 800 meters deep at least. And if we take a look at, for example, erosion level in southwest US, that's why we don't have many lithocaps left in southwest US. They've all been eroded. And of course, some of these lithocaps, like at Onto, like at Filo do Sol, those lithocaps actually overprint the deeper porphyry. So they can extend deeper. I'm only going to discuss one example here quickly, but I'm going to suggest that much of this shallow extent, including Grasberg, is simply incorrect. There's a paper published suggesting the potassic alteration at Grasberg that's outcropping before it started being mined was formed only 200 meters depth. That's 500 degree temperature biotite forming only 200 meters depth. It's impossible. There would have been so many phreatomagmatic eruptions that it would completely destroy it. Recent studies by a couple of different labs suggest that, top of Grasberg exposure probably is at least 1, if not 1.5 kilometers paleo depth. So it's Grasberg here rather than forming here in terms of the top of the porphyry. So that's just some bit of background. This is the porphyry system. And the reason I take a look at it, because there's been a lot of variety of studies. They've looked at the early A types of veins, the transitional molybdenum-rich veins, the later D veins, overprinting D veins with wet mica halos, commonly quartz pyrite halos. And of course, every porphyry is different in terms of its style of veining, its overprinting. We see here at least 6 styles of overprinting from this particular study from Zurich. And again, another reason for presenting Bingham is because there have been people, Jeff Keith and his students, as well as Keiko Hattori and Jeff Keith, where they argued that there was a stratovolcano over the top of Bingham based on a lot of volcanological studies and mapping here on the margins of the center of Bingham, with mafic dikes cutting the porphyry that only more recently have been recognized as being timed. They are syn porphyry and probably were very important to the formation of Bingham. Now, Bingham at depth has hypersaline liquids. Therefore, there must have been vapors discharged. And so Bingham volcano, however high it was, 1.5, 2 kilometers, it must have had a lithocap of quartz alunite alteration, etc., but it's now been removed. And those gases, we know they're related. For example, at Miyakijima, in a 3-year period, there were 18 million tons of sulfur as SO2 discharged, even though from this basaltic eruption, even though it was only passive degassing. There was no basalt erupted. It was simply vapors with a lot of SO2. So we know that there was tremendous amounts of sulfur erupting, and if any of this gets condensed with the vapors, it's going to be forming sulfuric acid condensates, leaching the rock. So that's just sort of setting the scene. I think most people, as I said before, now accept that there's some type of edifice, maybe not all stratovolcanoes, maybe they are domes, etc., like in the Yanacocha district, but these are certainly porphyry systems had an active signature at the surface, volcanic-wise and magmatic hydrothermal-wise. Any questions or comments, arguments? Anybody want to disagree?
There is a question.
Yes.
Dr. Miguel Ponce asked, why do we have zonations in high sulfuration system with silver-rich lateral zones chloragidite dominant, and gold-rich areas apparently near to core. Is it a matter or secondary enrichment?
Yeah, I have to think about that. I guess back up. First of all, we know that there are some, in lithocaps, there are some very silver-rich lithocaps. I mentioned earlier, Veladero, La Coipa, 100 to 1. There are also others that are close to 1 to 1, maybe 4 to 1 silver gold. Then the question about what about within a single lithocap, silver zonations. I guess if you have that, I've not seen it clearly in the lithocaps I've looked at, but of course, many of the lithocap hosted deposits I've looked at are supergene oxidized. And so then you have all of the supergene possibilities of perhaps moving silver and not gold, or vice versa. And when it comes to supergene, I have to confess that I know nothing about supergene alteration, supergene mobility of metals. So I'm not going to say much about supergene. And I guess I would have to ask the question, is it a zonation in silver-gold ratios in the sulfide or in supergene altered systems? Because if it's supergene altered, then of course we've got another factor, another variable to consider. So
there are no more questions.
Yeah, we can come back. We can come back to that a little bit later. I'm sure I didn't answer the question adequately. So I'm going to move through this very quickly because many of you are already familiar with porphyry systems, alteration, veining. For some of the younger students who maybe have not seen one, I'll just mention it, that we have a variety of porphyry events. Early high temperature veins cut by other veins, some of which are bringing metals into the system. There's a big argument about whether or not early A-type veins have copper brought with them at that stage, or if they're actually reopened and copper brought in at later lower temperature stages. At far southeast and Batahijao, there's some recent publications where copper is shown to be reintroduced along, as you can see here, an early vein has been, fairly early vein has been reopened with copper along the center line. That's not the purpose of this lecture, so I'll just move on and note that wall rock, of course, is going to host all of the possible veins, as well as the earliest porphyry, shown here in purple. But then we sometimes see intermineral porphyries, early interminerals, where they might cut off some of the earliest A veins because they come after those earliest A veins. And you may actually find refractory quartz veins there. But then there are later A veins that are cutting through this later, this intermineral porphyry, but then cut by a late intermineral porphyry that may in fact be also, though still cut by late or intermediate B veinlets and late D veinlets. This diagram from Dixoto, then modified by Massimo Ciardia. This is a sample from underground at El Salvador that I collected quite some time ago. And there are two intrusions here. I'll ask the younger students how we're going to distinguish the different intrusions here. We take a look here. And of course, it's easier if it's face-to-face, in-person audience. But here we see a intrusion with finer phenocrystales. Here, coarse phenocrystales. Then we think back to cross-cutting veins. Well, let's see. Here's one vein that's early. It's offset here. We go here, and then suddenly, right there, it looks like that vein is cut off. Also, it looks like that might be a xenolith of vein. It could actually be a xenolith of vein cut from there. If so, well, clearly this is a vein xenolith. This intrusion must be younger than this intrusion. This cut through and cut off some of these early A veins. So those are the types of observations that must be made to finally find the timing of all of the different veins. Basically, what cuts what, both intrusions as well as veins. So that was just a quick introduction to porphyry veins. And the bottom line that I want to point out here is that there are a variety of different veins here. Pepe Pedro recognizes biotite-rich veins cut by an early biotite-rich veins cut by a early A veinlet. There are magnetite-bearing veinlets magnetite veinlets, in here cut by magnetite-bearing A veinlets, et cetera, and molybdenite-bearing veinlets and late D veinlets. But the main point is the group mapped the vein density. And vein densities, typically, unless they were all late post-mineral D veinlets, vein densities show up very nicely as mapping out higher grades. Here we don't have grades, but this is where you can see at Las Preliminaries, this is where the open pit is. And obviously the open pit is going to be on where the higher grade part of the porphyry is. And as you can see, they are targeting the area that has the highest vein density, up to 40 veinlets per square meter. So this was just one example that I wanted to stress, that mapping out the veins and then also determining vein densities are critical. Then another aspect is zonation. Now, it's very dangerous to generalize about zonation of epithermal or zonation in porphyry, but the one thing we can say is that alteration is zoned, even though it may not be a simple repetitive type of zonation. Here at El Teniente, we see zonations, but we see alkali feldspar hosted by the mineralized porphyry, with wall rock having potassic alteration as biotite. So there we actually see zonation in the potassic alteration, depending on the intrusion or wall rock. And then a variety of other types of alteration with sericitic alteration, but also, let's see, green, where's the green? Oh, potassic propylitic transition on the margins. But then here at Hugodamit deposit, Oyotogoy in Mongolia, we have this sericite. We also have chlorite sericite over potassic. Well, it's quite possible that this sericite has totally overprinted really potassic, so you can't even see it, because we do see some chlorite sericite overprinting potassic. Now, advanced argillic was mapped here, and this is a point that I want to stress, that we have to be careful about using the term advanced argillic, because this is actually perophyllite. And getting to Zahira's point, well, here we have sericite transition to perophyllite. That is not the same as perophyllite in a lithocap. So probably the lithocap at Oyotogoy has all been eroded, and this has also been turned on the side. So we see sericite transitioning to rhyolite due to cooling. So, and there's also a lot of zonation here at Chuquicamata, different styles of zonation with sericite over potassic. There's potassic biotite. There's a study that's just been done on the deeper alteration here. I'm hoping that it gets published as the thesis. It's been just finished. That shows some tremendous temporal zonation patterns as well as spatial. So the point is here, we must be very careful about mapping alteration, mapping mineralogy. Don't just map it as potassic, philic or sericitic, advanced agylic. Map the minerals and look for overprinting relationships. And here we have these names with the minerals that fall within these groups, but again, maintain the mineralogy. Avoid these generalizations, because the generalizations, particularly when there's a complex overprinting, will start to get into trouble. I've seen interpropylitic mapped. Why? Because there's chlorite, which is a green mineral that some people call propylitic, but it's not. It's chalcopyrite related chloride alteration. We should not be using the term propylitic or interpropylitic to describe that. Keep the minerals. So that was just a quick review of that pet peeve. But now just let's take a look at a few porphyries that are, to a large extent, eroded below the lithocap. But still, there's some evidence there for that lithocap transition to the porphyry. And here we're going to take a look at Barahicho. The first of these 4 giant porphyries, world-class porphyries, discovered in the Sunda Banda Arc. Originally, Sumbawa Island was written off for porphyry. It was Newmont was exploring for epithermal, but fortunately they were also were sampling for copper, and they found a copper anomaly. So they followed the copper anomaly and gold anomaly up a stream until they come to a malachite waterfall and realized that they had something other than an epithermal prospect, and came up to the tops of the hills, discovered biotite magnetite outcropping with stockwork of quartz veins, but also zones which have been called advanced argillic at that time, but they are kelmite pyrite, or in this case, quartz elinite with local porphyry diaspore. This is actually just the roots of possibly a lithocap. This is a cross-section through the porphyry. The intermediate, the host rock diorite, the intermediate tonalite in orange, and in red was the young tonalite intrusion. Now, we use that as the background because now we're going to look at abundance of veins. Again, high abundance of quartz veins, greater than 5%, right through here. Moderate abundances of quartz veins, a little bit lower in that central zone. Possibly that that intermediate tonalite has destroyed some of the early veins. But then, from a surface point of view, there's the abundance of quartz veins at the surface, and you can see how closely abundance of quartz veins matches the copper grades. Now, quartz veins, here's a fairly early vein. We have a center line, but take a look that we also have some reopened structures cutting those early quartz veins with chalcopyrite and bornite. This is a paper that was just published last year by, I'm forgetting his name. He was a he was a Zurich, ETH Zurich PhD student. So we have at earlier studies there, we have the A veins, early A veins, some of the A veins being contorted, being deformed during the high temperature stage, 500 degrees, then cut by the younger veins with alteration halos. There is alteration halos to the A veins, but it's difficult to distinguish between the biotite K-feldspar of the A veins with Hanlens and the original host rocks. But clearly the lower temperature alteration has caused these later veins to have halos. But this is what Steve Garwin mapped in, he was doing his PhD thesis. Strong biotite in the core of the system at the surface, limit of weak biotite on the margins, the lighter brown, and then actinolite on the margins, almost the margin where the pit has extended to, and then a variety of green rock, moderate epidote absent, etc. And he showed that there was clearly some zonation in the epidote present, epidote absent. Subsequently, then he added in the overprinting white mica stage. And here we see in purple, we see intermediate argillic, a term I don't really like, cerussite, again, a term I don't really like, muscovite alteration following structures. And the paper by the recent Zurich PhD student has argued that much of the copper was introduced during this white mica stage. We also see some paragonite in orange, again, structurally controlled. And in the orange, and advanced argillic, but this is porphyroite. Now the question is, how much of this is white mica cooling porphyroite, or is there also some roots of porphyroite from a lithocap still preserved? I've worked in the district on the intermediate sulfidation veins, but I've not worked on this directly, so I can't answer that question. But you can take a look at the recent Badahijau paper. I'll send a copy of that, where it's argued that much of the copper was introduced during this white mica overprint stage. Now, or it may be that much of the lithocap, if not all of the lithocap, was eroded away, and what we're seeing here is porphyroite related to cooling of the white mica. Now, I promised at least a few geophysical slides. And first, here's the extent of the chalcopyrite. The colors are not that great. This dark purple is greater than 1.2% chalcopyrite in that core of the system. The yellows are 0.6%. Blues, hard to kind of see, is less than about 0.2%. Where a chalcopyrite. Whereas the pyrite, the purples, or let's see, the purples here have the highest pyrite, 1.2. So that's the pyrite halo. And the light blues, well, the reds are about 0.8% pyrite. The light blues would be much lower, the greens and light blues. Well, that's important when we start considering chargeability. Here is chargeability gradient array, and we see two chargeable zones. One related to this pyrite core of maybe 0.8% pyrite, but then very strong chargeability anomaly related to the barren pyrite halo to the system. And here we see that in chargeability in section. So it's important to separate the sulfide mineralization, well, the sulfides, the copper sulfides and the pyrite and the barren pyrite from each other to be able to really subsequently interpret your chargeability anomalies. I think I left out the magnetics on this, but of course we still have quartz biotite magnetite, so there's a magnetic high here that we don't see at far southeast, which I think I may have actually turned off out of this particular argument. So that's a porphyry that is essentially has had its lithocap eroded, but really we're right at the top of the white mica transition to perovskite. Here at El Salvador, it's a different situation. Guston and Hunt did extremely nice job of identifying the subsurface zonation here, muscovite and lucite alteration, overprinting of biotite. But there was, because this porphyry was discovered so quickly after identification, Anaconda didn't do very much mapping of the surface. And so my colleague, Yasushi Watanabe, spent 2 field seasons here mapping the surface alteration, and we compared that with subsurface alteration. And what he found was a zone of proximal perovskite. Now, this perovskite was argued originally by Gustafson and Hunt as being related to steam-heated alteration, acid fluids heating coming down into the system. But in fact, as we showed, that's definitely not the case. Here is Guston and Hunt's subsurface distribution of alteration and sulfides. There's a late low sulfide intrusion, the relatively least altered intrusion, with bornite chalcopyrite and more distal chalcopyrite pyrite zones. In outcrop, we see mainly chalcopyrite pyrite, not in outcrop, but in encapsulated sulfides, because of course this has all been supergene oxidized. So again, the pyrite, bornite, chalcopyrite, chalcocite zone at surface of El Salvador is encapsulated within quartz veins, because most of the, essentially all the sulfides have been supergene oxidized, unless they're encapsulated in quartz veins. And then taking Guston and Hunt's muscovite distribution and andalusite alteration, along with Watanabe's surface andalusite and muscovite alteration, because this is section and this is outcrop, so this is like a cutaway. And then integrating with subsurface perovskite and surface perovskite, and looking at Watanabe-san's white mica perovskite in SEM. As I mentioned earlier, muscovite that is replaced by perovskite due to cooling actually is intergrown. And the white mica here has a lower molecular weight, so that's why it's lighter colored in the SEM view, and the perovskite has more silica, much more silica, so it is darker, and you can see it's just an intergrowth. And so if you see that kind of texture in thin section or SEM, the argument would be that perovskite is a replacement due to the cooling of the white mica. Hopefully that helps to answer partly Zahira's question. And as we've already pointed out, the argument is, I'll get to that, but here, this is how we get into basically a cooling hypogene condensate. As it cools, it becomes more and more acidic because more acid is to the left of this diagram, and we get into the residual quartz zone, the lithocap zone. Less acidic, we're analyte or diaspore pyrophyllite. But we're going to cut that out of the picture now. If we don't have the lithocap, if we simply cool a fluid from K feldspar stability through andalusite, and clearly we have very nice andalusite muscovite at El Salvador. And so the fluids are cooling andalusite muscovite, and then they got to a point where below 350 degrees, those muscovite stable fluids became pyrophyllite stable. And that's when the muscovite andalusite started to convert to pyrophyllite. And so that's why the pyrophyllite that Watanabe-san mapped with shortwave infrared and hand lens over the top of the El Salvador is largely pyrophyllite related to the cooling of the white mica system. And it even cooled further on the marginal systems from pyrophyllite to even dicite. Below 300, 250 degrees got into dicite stability. So those were not lithocap minerals, those were white mica cooling. Stressing the importance of knowing these different acid environments of acid alteration. So this is that white mica cooling, and that's why we actually get patchy pyrophyllite of siliceous-rich rocks, because to form pyrophyllite, we need a lot of silica. And the only way to do that, and what it gets the silica, is by nucleating in that silica-rich base of the lithocap and start to form the patches. So this is what El Salvador looks like now. Of course, there was biotite, chalcopyrite, bornite at about 41.5 million years here, but that's all been overprinted. Well, at that stage, there would have been a 41.5 million year zone or lithocap of residual quartz, halo of quartz alunite, just like we had or have at far southeast with the 1.4 biotite and the 1.4 million year alunite, but that has basically been eroded. It was, first of all, overprinted by 2M1 muscovite and andalusite. So a lot of the biotite was overprinted. Of course, once it was eroded, that chalcopyrite bornite is completely supergene oxidized. So we only see this chalcopyrite bornite where it's encapsulated in quartz veins at the present surface. And then continuing with that 41.5 million year overprint by the 2M1 muscovite. As a 2M1 muscovite, as those liquids cooled, they basically rose into the pyrophyllite stability. So that's why we have this pyrophyllite zone, and that's the extent of the pyrophyllite zone mapped by Watanabe-san over the top of El Salvador. That's not related to the lithocap. However, to make it more complicated, here in those cliffs are quartz alunite. Well, how do you get quartz alunite down when you said that it was up at this level? Well, our initial samples of alunite that we sent to be dated when we did that original work at El Salvador in 1998 or so, those were lost by the laboratory. But subsequently, we were able to get more samples of that quartz alunite. And Antonio Ribas, we had no more budget, but Antonio Ribas fortunately had some free money. And so he dated those samples. And those alunite samples that are in that quartz alunite zone, replacement zone, come out at basically 38.0 million years. Plus or minus 0.5, 2 million years, 3 million years younger than the biotite. So this is a younger lithocap. There would have been 3 million years of erosion, and this quartz alunite here, barren, is basically related to this younger event. There must have been a younger intrusion at 38 million years in the system. Very much like the Escondida system, where you have Papa Escondida and Escondida Este, deeper, actually a lithocap overprinting Escondida that is younger than Escondida, related to the younger, 2-3 million year younger intrusive systems where formed deeper porphyry systems and very well mineralized porphyry systems. So there has to be an intrusion, younger intrusion here at El Salvador, and possibly mineralized zone. So that's how we explained this younger, much younger quartz alunite barren zone, not only quartz alunite replacement, but also these dikes that of porphyllite, diasporic dicite that Guston and Hunt recognized, but they argued those were related to steam-heated descent of steam-heated alteration. Those are actually porphyllite, but much younger than the original El Salvador system. So, and as I said, we see that at Escondida, and now more and more systems around the world where there's a evolution over several million years and a falling of the erosion of the paleosurface such that any young lithocaps may indicate potential for the for deeper porphyry systems like Papa Escondida, Escondida Este. And there may be questions, or people may be shaking their heads. Anybody, probably there are some people who've worked more on El Salvador than I have. There, any questions?
There are no questions, Doctor.
Okay, well, we will continue this because it does continue, and we'll entertain any questions at the end. One of the best examples of lithocap overprint of porphyry is that Filo de Sol. Of course, that is still being studied, so I'm not going to present anything on that, but take a look at a published study here by David Burrows of the Onto in Sumbawa, the Onto lithocap overprinting the deeper porphyry. A world-class 1.7 billion ton and growing. It's probably going to be, based on unpublished numbers, could be as much as 3 billion tons of 0.9% copper, 0.5 grams gold. These are in resources. Heavy jungle in this area, and with very large lithocaps at the surface. Much of this part of Sumbawa is covered by lithocaps, residual quartz, alunite, kaolinite, etc. The lithocaps are up to about 400 meters thick. They basically are sterile, but there have been ferromagnetic eruptions through the lithocap, diatremes, that have brought up porphyry copper fragments, a little bit like at Kimzacocha, but these porphyry copper fragments were very well mineralized, and it was these porphyry copper fragments that actually caused the stream sediment anomalies in copper. If it wasn't for those diatreme transported porphyry copper fragments, there may have been no stream sediment anomalies in this area. So please have a look at Dave Burrows' paper in Economic Geology 2022, which received the Brian Skinner Award. And here, very briefly, this is the last example we have. Here we have capping andesite. And that capping andesite is not pre-mineral, it's probably syn mineral. Below that is a USP. We have basically have three early intrusions: the early porphyry in red, the early intermineral porphyry in purple, and then late intermineral in orange, outlined here in white. This fragmatic breccia, which actually is not present on this section, it is on other sections. And then alteration. I'll back off. Well, I'll leave the intrusions. So this is the extent of the intrusions. The capping andesite altered to illite smectite. But at the base of the capping andesite, there is porous residual, vuggy residual quartz. There's also quartz dicite in orange here. There's massive residual quartz, silicic. And this is all to 400 meters depth. This is all basically sterile. There's also quartz alunite in sort of pinkish, light, pinkish color. There's quartz pyrophyllite alunite in the browns. There's quartz diaspore pyrophyllite in the dark red. This is a huge overprint of lithocap style of alteration over the top of the porphyry and the porphyry related intrusions. And this all took place, the oldest ages here, 0.4 million years, 0.4 to 0.2. So extremely young, extremely rapid erosion and overprinting of the lithocap over the top of this porphyry. Here we see vuggy quartz right through here, sterile. Here, AB veins. You can see the AB veins here overprinted by a vuggy overprint, but with 2.5% copper, 1.5 grams gold. Here, that's 190 meters elevation, about here, 140 meters elevation, about through here. More AB veins, 1.1% copper, 0.9 grams gold. Here, quartz pyrophyllite alunite with this characteristic patchy textured pyrophyllite replacement of quartz alunite. And here, let's see, I forget where, that is also here, 4.6% copper, 1.3 grams gold. Basically, high-grade copper and gold mineralization associated with, as you can see here, high sulfidation state covellite, overprinting the initial porphyry associated with quartz pyrophyllite alunite. And in other places, you can see pyrophyllite alunite intergrown with covellite. So the covellite here is syn pyrophyllite alunite. You can see the alunite intergrown with covellite. So, a tremendous system. The details haven't been studied yet, but it just shows that you can actually have a barren lithocap where the surface of the lithocap is barren, but the roots, possibly older lithocap, is overprinting the somewhat deeper porphyry, all within a very short period of time. And Dave Burrow's paper, they have a lot of rhenium-osmium dating on the mineralization itself, as well as argon-argon on the alunite and uranium-lead on the intrusions. So it's a very nice story, but it's very complicated because of the overprinting, and there'll be many studies done here in the future to try and sort this out. Alternatively, take a look for a relationship to the Andes. Take a look at the paper by Perio and others just published, last year, or is it already this year? I can't remember now, 2023 or 2024. But a very nice paper on Filo del Sol and the lithocap overprinting porphyry there. So this is basically the level of sterols. There's several hundred meters of sterile lithocap and capping illite smectite volcanic rocks, andesites, over the top of this lithocap here. It's only the diatreme-related breccias that gave some hints to what's deeper. And just quickly relate to this. Now, here, a lot of lithocaps go into nargite and then back into late chalcopyrite. But here, in nargite and chalcopyrite of Onto must have been related to the fact that there was so much leaching of the rock that there was no buffer capacity at all. And that's why there's so much chalcopyrite in this Onto system with such high grades. So the last slide. This is only very brief discussion of that base of the lithocap into the tops of the porphyry. We looked at it at Yanacocha, Kupfertal, at El Salvador, and now at Onto. But if you come across a lithocap, even if it's sterile, first thing to do is ask the question, are there any marginal veins? We didn't really discuss that in this series lecture, but we did talk about the name of the what was the name of the, I'm forgetting right now, the name of the diatreme hosted, which is now San Gabriel. It has names changed 4 kilometers away, 9 million ounce diatreme related intermediate sulfidation system on the margins of essentially sterile or low grade lithocap. And if you have a lithocap, don't necessarily drill through it, because as we showed at San Jose and on the margins, the shoulder of Kupfertal porphyry in Yanacocha, same age lithocap sitting on the margins, not directly over the porphyry. So you want to get into the deep valleys, look for any evidence, look for the possibility of stockwork veins, look for any other evidence, white mica to porphyry transition, et cetera, and on the basis of that, then test those targets for deeper porphyries. If there is one below the sterile lithocap. Certainly, lithocaps indicate potential for in places for lithocap-hosted epithermal, but if not, we still have to think about the other possibilities of marginal epithermal veins or deeper porphyries. And of course, that requires evaluating the level of erosion. Are we just at the base of lithocaps, like probably occurred at El Salvador, or are we even deeper, like Southwest U.S. porphyries? Or do we have a younger lithocap that's overprinting a porphyry, suggesting there may be even deeper porphyry potential, like in the Escondido district? I think those are the last of my slides for that very, very quick run through. So if there are any questions, I'll be glad to discuss them.
There is a question, Doctor.
Yeah, I see that Aldo has asked a few general questions about Andean region lithocaps from the front of the arc more favorable to overprint porphyry copper deposits. So are there more high grade? I guess I would have to ask the local experts that question and turn it to Aldo. Do you think that that is the case? That the front of the arc is more favorable? I am not a tectonics. I tend to work on prospect-specific targets as opposed to considering these more tectonic scale questions. And that's why I leave these tectonic scale questions to the people who look at them, both conceptually, like Massimo Ciardia, as well as people in the field considering those things. I wouldn't want to even address that question. Aldo, do you have any suggestions? And also, you asked, are the frontal arcs have faster erosion rates? Well, it all depends on the nature of the tectonics and its uplift rate and erosion rate. Again, I have no experience in that area.
Okay, hello, Jeff. Thank you very much for your answer. I would say yes, probably we have more chances to have sector collapse or erosion of lithocaps in the front of the arc, maybe, because you have more these deep eroded valleys in this area, and probably you have more. I think there are a couple of papers of Thomas Bisi addressing this situation, these settings. But I'm wondering about this. I'm not totally sure.
Well, the person to ask would be somebody who's done a lot of work on uplift rates and erosion rates would be Dick Silito. He just posed that question to him sometime. He might either have a simple answer or he might say, well, he'd have to think about it or actually do some investigation. I mean, at a previous short course I gave, somebody asked me, actually at PDAC early this year, someone asked me, what about lithocaps related to alkalic porphyries? Are there lithocaps? I said, well, I've never worked on an alkalic porphyry or a lithocap that I knew was related to alkalic magmatism. So I asked Silito that question. We started discussing it. And a week later, we started writing a paper, and we've now submitted that paper for consideration. And bottom line is we found that there's a lot of evidence for lithocaps related to alkalic magmatism. And in fact, there's the lithocap style alteration preserved around at least 3 or 4 alkalic related to high sulfidation deposits as well as porphyry deposits. So I can go back and answer the question at PDAC. Yes, there are lithocaps related to alkalic. I can't answer your question. I have no knowledge of uplift rates, erosion rates, but if you present it to someone with that knowledge, like Silito, he may consider it. And particularly, it might be something that Massimo Ciardia would consider. I'm not sure how much he works on uplift rates. You may know some of his papers better than I, having also coming from Geneva. But have you seen anything that Massimo works on uplift rates?
No idea. No, I'm not sure. I'm not sure.
Okay.
But thank you very much for the answer, Jeff.
Well, it's not an answer. It's just a discussion. I'll have to think about that. And as I say, at least in terms of alkalic related lithocaps, I had some ability to answer that because that was a question that we looked at. So interesting questions, and those questions then might cause some of us to ask why or why not.
Okay.
I'll try and look into that and let you know if I find any question and if I find any insight. Okay.
Okay. Thank you very much.
Well, we have gone over by 45 minutes. Anybody else? Anybody?
Hello, Jeffrey.
Yes.
It was good, your presentation. My question is, I don't know if you work in Archean or Proterozoic porphyry systems. No? Just I wanted to know if there is any difference between these really old porphyry systems and young systems.
There's a lot of, it's like a lot of the questions. There are some people who say there's no such thing, but of course there are. In fact, in northern Sweden, the Aitik Paleoproterozoic porphyry, it's been, metamorphosed some and whatnot, but more and more study that I see coming from that suggests that, it has a lot of similar characteristics, but they have been overprinted. And I've not looked at them directly. I've just glanced at some of the papers. So you'd have to ask, there's some people who've published on Aitik porphyry. You'd have to ask them those questions to get a good answer. It's clear that once you have subduction, you're going to have all of the parts necessary to cause dewatering of subducted slab, partial melting of the mantle wedge, starting to form thicker crusts and building up magma chambers in the thicker crust, differentiation, eventual ascent and exsolution of those fluids. And as soon as you start having exsolution of fluids, you should start to have some mineralization. And as soon as you have separation of those fluids, you should have vapors coming up and causing lithocaps. There certainly are lithocaps that are neoproterozoic, and two lithocaps that one of them I've looked at and the other one I've read about in Phanoscandia, they are paleoproterozoic. The paleoproterozoic lithocap was called metamorphic gold deposit, but in fact it's just a metamorphosed lithocap with silmonite and andalusite halos. Well, that's simply metamorphosed halos of porphyllite or dicite or kelnite. So going back to the Paleoproterozoic, we certainly had lithocaps forming. We had those types of systems already related to subduction. So, I mean, that's about the only comments that I have to make about those aspects without really having any experience with those. So if you're working in the Paleoproterozoic, keep looking for preserved areas. Lithocaps themselves indicate already shallow preservation. So I was asked about how do you distinguish Paleoproterozoic lithocap? Well, you start by looking at green schist facies metamorphism, large areas of green schist and if you start finding small areas of higher grade green schist facies, higher grade metamorphism, it may be higher grade because the rocks were already leached and aluminosilicate only. Because if you take aluminosilicate rocks up to green schist facies metamorphism, you're going to start forming higher grade minerals just because the host rocks were aluminosilicate rather than normal rocks. So that would be one thing if you happen to be working in Paleoproterozoic terrain of green schist facies metamorphism. And I never have, but that was just a conceptual argument.
Okay, thank you so much for your comments.
Yeah. Any other questions? Or is it, it's almost beer time in Lima. What time is beer time in Lima? 6 o'clock?
No, it's 5.
5 o'clock beer time in Lima. Okay. Diego, Zucker, are you going off and having a beer now?
We have a more question about Ricardo.
Yeah, if I can.
He has his hand up, see?
It's about 1 o'clock by night here in Italy. So thank you very much for the presentation. I will enjoy something stronger now. Anyways, so just a couple of points. It's, I think, for the students more than anything, keep in mind that the structural geology plays a role that is critical always, because the pathway for the fluids are fractures, essentially, and major faults. So you can have telescopic intrusions. For instance, I've been working on some porphyries back in the time, essentially in the Laramide, northern Mexico, and southern Arizona, where the systems were just barrier of low-grade porphyries and telescopic intrusions with high-grade moly, piercing a former copper porphyry. Yeah. So that was very interesting. Not gold at all around, unfortunately, but it's good to have a look at the overprinting and the different type of alteration that those pierces may experience. Yeah. And this can be a mess. You can end up with 100 different type of alteration, and then you realize that it's just a progressive history or superimposing stuff. And the other thing, I'm from Italy, in a region where there's an active geothermal field, where there's 3 actually. So what we have here is lithocaps forming, but so far we have very shallow magma chambers, as shallow as 3 kilometers, but no deposits. What we have is massive sulfide, like pyrite, chalcopyrite, and this kind of stuff has been mined for centuries. Now there is not a single metal mine in Italy, but this is a sad story. So you can have, actually forming lithocaps, but no deposit. Not yet, or not deposit.
That's like at Sasamijima. And are you aware that Volcano is an actively forming lithocap? La Fossa at Volcano is, papered by Fulignati, 1998. He describes lithocap-related mineralization, lithocap-related alteration on Volcano. La Fossa, if you've ever visited La Fossa.
Oh, no, not really.
Well, I want to go visit someday. So, Ricardo, ¿habla español?
Sí, claro.
Sí, por favor, repita en español, en estructura.
El apunto en la geología estructural, no más es porque los fluidos quieren pasar de alguna ruta que está más fácil, y está más fácil donde la roca está quebrada, y está quebrada por fracturas o por fallas. Entonces tiene que darse cuenta de la que es la situación estructural. Muchas veces hay, no sé, cosas como Pulapart o como zona de cizalla, que pueden ser el corredor preferencial para la subida de fluidos, y ahí se meten preferencialmente. Entonces, si van buscando lo que es el feeder del mineral, esta es buena idea enfocarse mucho en lo que es la geología estructural. Pues muchas veces hay un cuerpo que puede ser distinto por un lado del otro de una misma falla, de una quebra, y ahí en el medio mero está el bueno, está el choque. Entonces, pues tienen siempre que darse cuenta, conocer la roca está completamente quemada por la alteración, mapear la alteración por mineral, como justamente digo el doctor, y darse cuenta de lo que es el patrón estructural. como consejo de trabajo, ¿no?
Muchas gracias.
Obrigado. Bueno, muchas gracias a ustedes. Muy buena presentación. Y gracias por organizar no sé cómo yo terminé en este grupo, pero me gustó mucho la presentación. Muchas gracias.
No. Ricardo, if you send me an email, jhedenquist@gmail, I can send you a paper on lithocap forming today at Volcano.
Yeah, sure. Thank you very much. I will appreciate it.
Okay, so yes, Diego, Sucre, everyone else at UNI in Lima, and everyone else who has joined in, thank you very much for staying around a little bit later for your questions, and hopefully another SEG student chapter in the region will organize another short course, half a day or 1 day, and invite everybody in the region to attend. And possibly next time you can get someone who can give you a lecture in Espanol, Antonio Rivas, et cetera. So anything else, Sucre?
Yes, dear Jeffrey, I think that's all for today. We really appreciate that you have taken the time to hold a conference for us. We want to give you a recognition, that is a certificate. Diego, can you share your screen, please?
Yes, Doctor, can you stop to sharing your screen? Yes, please. Thank you.
So everyone can turn off their camera, please. I will take a photo. Please, todos pueden prender su cámara, porfa. Por favor. Un momento.
Okay. Sucre, are you going to send a certificado to other people?